The next few presentations, I want to walk you through some concepts and some details exploring the idea of a synapse. You know that a synapse is the connecting point either between a neuron and another neuron, or a neuron and a muscle fiber. Could be smooth muscle, could be skeletal muscle. So a chemical synapse is basically one where the way that one neuron will talk to another neuron or talk to a muscle fiber is by the release of chemicals called neurotransmitters. So the neurotransmitters are being released from a presynaptic terminal and will bind to receptors on the postsynaptic terminal. So one of the things that we're going to do here is going to be using the neuromuscular junction as an example. A lot of times you'll hear it neuromuscular junction. It'll be in NMJ. So we're going to use this as an example to see some of the behavioral characteristics of a synapse. So we'll use this. So what we have here is a motor neuron, and of course you see little cartoon there symbolizing myelin and the nodes of Ranvier. And then you have a neuromuscular junction here. And the neuromuscular junction is there. We have a series of zooms here. The neuromuscular junction, compared to a synapse between a neuron and neuron, is hugely different. The neuromuscular junction is literally thousands and thousands of times larger than the synapse from neuron to neuron. You have to have electron microscopy and blow things up 10, 15,000 times to see a synapse from neuron to neuron, whereas the neuromuscular junction, you can see it under low power light microscope. So they're a universe apart in terms of size. As far as this is concerned, if we just kind of zoom in here, you got that's your neuromuscular junction there. So you see the myelin, and you see, again, these little presynaptic terminals here. And then you got a zoom right there, and this is going to be your presynaptic there, and this is your postsynaptic here. Now, the postsynaptic in this instance is going to be a skeletal muscle fiber. So what we have is we have these little circles here, and those circles are going to be symbolizing synaptic vesicles, and within the vesicles will contain neurotransmitters. You have in the cartoon here some mitochondria. Mitochondria play a very important role in presynaptic terminals in terms of generating ATP, and also involved in other aspects of presynaptic physiology. You have here in the cartoon a dense bar, active zone. All that is a collection of various proteins that are going to draw the vesicles to the membrane so that they can be released. We'll get into a little more detail on that later. On the skeletal muscle fiber side, or the postsynaptic membrane, we have these acetylcholine receptors, and I'm going to put a little in there because these are actually nicotinic acetylcholine receptors, and they're waiting for the neurotransmitter to be released. And in this case, for a neuromuscular junction, the neurotransmitter is going to be acetylcholine or acetylcholine, can say it either way. So the released acetylcholine will bind to these nicotinic receptors, and then we'll talk about what goes on after that in a moment. Okay, so acetylcholine is going to be the neurotransmitter of choice for a neuromuscular junction. When it's released from the presynaptic terminal, it's going to cross and will bind to, again, nicotinic acetylcholine receptors. These acetylcholine, the acetylcholine itself would be considered the ligand, and of course the ligand binds to the receptor. So here's a cartoon here of an acetylcholine receptor, a nicotinic acetylcholine receptor. So we'll go N, A, C, H, R there. It is a channel. So when the neurotransmitter binds, in this case this is going to be acetylcholine, and I'll amend the cartoon a little bit, because for the nicotinic acetylcholine receptor, you actually have to have two acetylcholines to bind to it before it'll open up. So you have one bind there, maybe one bind there, and then upon binding, it will, in this case, open the channel up. And when it opens the channel up, it's going to allow potassium to leave, and it's going to allow sodium to come in. So this is inside membrane and outside there. And as we've seen before, you have lots and lots of sodium here and a little bit of sodium inside the cell, and then you have lots of potassium inside the cell, a little bit of sodium outside the cell. So whether or not, or the movement of these electrolytes in terms of direction that they go, is simply going to be a function of two things. One is the Nernst value for each of these electrolytes. We've talked about that before. And then the other is what's the potential associated with the channel itself. So with skeletal muscles, it's very negative, usually around 90 millivolts. Neurons tend to be around 70 millivolts, but minus 70 millivolts. So the neurons, the postsynaptic membrane is very, very negative. Well, if it's very negative, then that means it's very close to the Nernst value for potassium. So even though the channel is open to potassium, you don't have any real electrochemical forces acting on potassium to drive it out. So where you have all your forces is working on that sodium. So sodium is sitting out on the outside, so you got a big concentration gradient, of course, so vector there. But also you have a huge electrical, because the Nernst value for sodium is like around plus 60. Well, the membrane's sitting at minus 90. So I also have a fairly healthy electrical force drawing the sodium in. So again, sodium is going to rush in in preference to potassium leaving. Now, another thing they left out in the about this channel here is that the nicotinic acetylcholine receptor is also somewhat permeable to calcium. So it is possible for calcium to also go into the postsynaptic membrane. And as we know, calcium is a second messenger. So if you have a situation where enough calcium is going through there, you're actually going to be starting to have all sorts of biological effects in the postsynaptic membrane structure that's going to be associated with elevations of calcium. So that's kind of how that is working. So let's see what we have here. When the membrane actually is going to undergo depolarization, and it might go from minus 90, maybe, I don't know, up to plus 60, we'll just do round numbers. And so when it's at plus 60, now the potassium is the one that is most unhappy because it's farthest away from the resting membrane potential. So if it's sitting around plus 60, then that means most of the current through these channels, if they are still open, is going to be potassium effluxing. So you have that. The amount of neurotransmitter receptors, nicotinic receptors on a motor end plate is 10 to the 7th. So again, we're talking a lot of receptors because simply of just the size of the motor end plate. Let me say a couple of other things about the nature of these nicotinic receptors, acetylcholine receptors. You will recall when we were doing axons and we were talking about the voltage-sensitive sodium channels and how they have three states. You have a resting state, active state, and inactive state. And we saw that when the voltage-sensitive sodium channel was depolarized, that opened it up, sodium can rush through. But remember, it's double gated, so it would open up for a very brief period of time, and then the H gate would slam close. Okay, that's the inactivation gate. And then that channel is blocked. It won't allow any more sodium to go through until what happens? Until the environment around that voltage-sensitive channel has then gone back to baseline resting membrane potential. Then it goes from an inactive state to an active state again, a resting state. Therefore, it's open for business again. So you have that cycling going on. You have something actually fairly similar with the nicotinic receptor as well, the nicotinic acetylcholine receptor, in the sense that it also has a resting state. Okay, resting state means it's open for business. It's open for acetylcholine to combine to it and electrolytes flow through. Then it's going to be an active state. Inactive is when it's actually opened up. And also now you have an inactive state as well. And so when it's inactive, and again, there's another gate that swings closed, now no electrolytes can go through. So if the acetylcholine is stimulating enough of the nicotinic receptors, it is possible to put them in an inactive state such that they won't become active again, or at least resting again, until the membrane repolarizes. So it works similar to a voltage-sensitive sodium channel. It's not exactly the same, but all my point is that if you have enough acetylcholine in the synaptic cleft and you really stimulate these receptors to a higher degree, you're going to put them in an inactive state, and they're going to stay locked down until the membrane is repolarized. So that's one of the characteristics of a nicotinic receptor. The other thing, too, that I want not to leave you the impression with is that there's one type of nicotinic acetylcholine receptor. You have many, many, many subtypes of these receptors, so they're not all the same. They all have different slight characteristics, so it is a heterogeneous structure that they have. They're all considered nicotinic, but they all have subtle differences. And nicotinic receptors, as we're obviously talking about here in the neuromuscular junction, but you've got nicotinic receptors throughout the central nervous system. You also have various subtypes of nicotinic receptors. So in one part of the brain, you'll have one type of nicotinic receptor. Another part of the brain, you'll have another part of the nicotinic receptor. And so how those receptors behave when a ligand binds to it can vary hugely depending on what subtype we're talking about. And since we are talking about nicotinic receptors, that means nicotine binds to them. And so in the case of if you're putting nicotine in your body, which means you're using tobacco products, you're flooding your system with nicotine, it's going to bind to these receptors. And when they bind to the receptors, they're going to have a downstream effect because you're altering the functioning of the receptors, particularly in the central nervous system. And again, the effect that it has depends upon what type of subtype of nicotinic receptors interacting with, which is tied to various brain regions. So anyway, so if one is smoking, one is bringing another player in that's having all kinds of interesting interference with the neurofunction in terms of your central nervous system. Another point that I want to bring up is that I don't want to pretend that the only binding sites, and this is true for most of the receptors we're going to talk about, that the only binding sites that the receptors have are the ones concerning the neurotransmitters we're talking about. There are multiple binding sites to all receptors, and it depends upon what drug we're talking about as to where it's going to bind. So you've got hormones that can bind to these receptors. You've got other drugs that can bind to these receptors, etc. So these receptors all receptors typically have multiple binding sites for multiple different types of bioactive molecules. So I don't want to oversimplify and say, oh yeah, the only binding site for this is acetylcholine. You have other binding sites for other things as well. So I just kind of want to review a little bit in terms of how an action potential would be generated in a skeletal muscle. We've talked about this before, but I just want to make sure we're all on the same page. You recall that you have, say, this is going to be a skeletal muscle fiber here. So it's also a post-synaptic membrane, of course. And then you have these little guys here. And so we're going to say that those are going to be my nicotinic acetylcholine receptors. So I'm going to have a, nicotine binding to these guys here, yes? Okay, but also in the neighborhood, you'll recall, I'm going to go here, 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 and here, and here, that these are going to be voltage-sensitive sodium channels. Yeah, I know we have voltage-sensitive potassium channels as well. But voltage-sensitive sodium channels is what I want to draw your attention to. So the idea is that the acetylcholine is released. It will then depolarize, this area here, going from minus, in this case, minus 90, maybe up to plus 60. And the depolarization, because why? Because sodium is rushing in through the nicotinic receptors there. Will depolarize this, and that will in turn bring these other receptors the threshold. In other words, the depolarizing event by the release of acetylcholine depolarize the membrane, which will then cause these voltage-sensitive channels to open up, allowing sodium to rush in there, and now we have that domino effect, as in one group of channels will open up another group of channels, which will open up another group of channels. So you have radiating out from the motor end plate will be action potentials, all started there. So that's, again, kind of the way how that works. We've talked about this before, but I just want to make sure that we're all on the same page on that one. Now, this is a principle that I have talked about maybe before, certainly we'll talk about it again, and that is if you're going to release a neurotransmitter, you have to have a way of controlling the level of neurotransmitter in the synaptic cleft. So if you release it, you have to have a way of making that neurotransmitter go away. If you want more, you'll release more. So one of the major ways that you control the amount of acetylcholine in or that's interacting with a postsynaptic membrane, whether it be muscle fiber or whether it be a neuron-to-neuron communication, is that you have an enzyme, acetylcholinesterase. ACE gives you a hint that it is an enzyme, and its role is to break down acetylcholine to its constituent parts. And I may have said this before, I don't remember, but acetylcholine is assembled, is synthesized in the presynaptic terminal. You have an enzyme there that's going to take acyl coenzyme A and is going to hook it up with a choline. And then when you bring those two together, you have acetylcholine. So that is synthesized in the presynaptic terminal. Then a vesicle, a little synaptic vesicle, has a little transporter in it. It's going to grab that acetylcholine and then we'll put it into the synaptic vesicle in the presynaptic terminal, and it's ready to go. So the acetylcholine is released, but as soon as it's released, you have acetylcholinesterase, which is associated with the postsynaptic membrane. Its job is to very rapidly tear down or tear apart the acetylcholine. So it will do so. It will break it down back into the acyl coenzyme A, which eventually gets turned into acetate, and then the choline. And now what will happen is that you have in the presynaptic terminal, you have receptors that will grab the choline and will literally transport them back into the presynaptic terminal. So the choline is recycled, whereas the acyl coenzyme A or the acetate is just metabolized away. So that's how you control the amount of acetylcholine in a synapse that uses acetylcholine for its neurotransmitter. Is you have an enzyme that is very specific to break it down very, very rapidly. So that's how you clear it out. So let's go back to a little more on the mechanism, exactly how a neurotransmitter is released. So I'll kind of zoom in here. We're going to walk you through the paces. So again, we have a presynaptic, postsynaptic. So it's going to be post, and this is going to be pre. Okay, so there are my little vesicles, and there's my little neurotransmitters. So I'm going to have an action potential that's going to propagate down. Now, as the action potential propagates down, associated in the presynaptic terminal are going to be little, I'm going to draw them here and here. These are going to be voltage-sensitive calcium channels. So the voltage-sensitive calcium channels, when the membrane in which they are residing are depolarized, those voltage-sensitive calcium channels will open up. And when they open up, calcium will then flow into that presynaptic terminal. So, and you can little arrow there, calcium will flow in when the membrane is depolarized, and at that point, these guys open up, allows calcium in. So after the calcium is in, and we're going to go into a lot more detail on this later, but the calcium is going to cause a series of events to happen in that presynaptic terminal that's going to involve some interaction of proteins, where those proteins are really actually going to take and grab the synaptic vesicle and is going to pull them towards the membrane. It will fuse with the membrane and will literally release their contents. And once they release the contents, and the contents then are free to bind to whatever receptors they find on the postsynaptic membrane. So calcium is an incredible player in how all this works. The voltage-sensitive calcium channel, again, they're heterogeneous as well. They're not all the same. But they can open, and some have estimated anywhere from minus 50 millivolts, and some of them are open even when the potential is in the plus range inside relative to the outside. So point being is that you have a group of voltage-sensitive calcium channels, and when the membrane becomes less negative, they begin to open, permitting calcium to come through, and then when calcium comes through, then stuff happens. So that's basically, I believe, what is going on, or what I've said over here in the verbiage. Whether this is neuron to neuron or neuron to skeletal muscle fiber, the presynaptic events and the voltage-sensitive calcium channels, it all works pretty much the same. So let's go back to this little drawing here just to make sure we're following it. So just because we don't have any confusion. So this is considered an action potential here. Okay, so we are measuring voltage change. I'm going to say delta voltage changes. So action potential. So this action potential we're reading here is associated with what's going on in the presynaptic terminal. Okay, so that's what that is. So we got the dot, dot, dot here. There's the delay. So this is time, of course. And then note what we have here. I'm going to zoom in. Again, a delicate point, but a point that's very important, which is when the neurotransmitters bind to the receptors, assuming the receptors are functioning as ion channels. And again, we'll learn in a bit that not all receptors are ion channels, but if we're talking about ion channels here, they open, allow depolarization. So the idea is to have an action potential on the postsynaptic membrane, in this case maybe a muscle fiber, or to bring the downstream neuron to action potential. So what that means then is that you're going to have a depolarizing event, but that somehow you're going to have that depolarizing event such that it is going to be affecting voltage-sensitive sodium channels in the postsynaptic membrane at some point, opening them up so that you can have then another action potential. So the idea is to bring the voltage-sensitive channels to threshold. In other words, to have enough of them open at the same time that you can start this domino effect of an action potential. So just to say, for instance, suppose there were no voltage-sensitive sodium channels in the neighborhood. So if you were measuring the potential on the postsynaptic membrane, what would it look like? Well, if there were no voltage-sensitive sodium channels in the postsynaptic membrane, you would have the neurotransmitter being released, in this case maybe acetylcholine, allow sodium in. So what you're going to get is going to be this. It's going to go up, and it's going to come back down. Now, this is called a graded potential. So it's like a light dimmer. And you can have varying degrees of graded potential. And that's going to be a function of how much neurotransmitter is being released, assuming that this neurotransmitter is excitatory and wants to depolarize the membrane. So you have a series of graded potentials. So, well, what's this over here then? We got this guy right here. What's that all about? Well, that is, in fact, an action potential. So we'll go action potential there. So this would indicate that the postsynaptic membrane has had some sort of action potential. Again, suppose it's a muscle fiber. Well, then what that means then is that then this postsynaptic membrane, if I have my voltage-sensitive sodium channels over here, and I've depolarized this enough to where I'm going to bring these guys to threshold and then just have action potentials that's going to propagate throughout the muscle fiber itself. So if I have the correct configuration of voltage-sensitive channels, which would make it an excitable membrane, I now can have an action potential. So it was the graded potential that allowed the action potential to occur. So the whole point of the graded potential is to bring these voltage-sensitive sodium channels to threshold so that you can then have an action potential. So the only way this happens is if you have a graded potential. And the purpose of the graded potential is to, in this case, bring it to threshold. And again, bringing to threshold means having enough voltage-sensitive sodium channels to open up. We've talked about this before, but I just kind of want to review this with you. Okay, last point on this block is, and I'm just making a clinical point here. There is a clinical condition called the Lambert-Eaton myasthenic syndrome. And I'll just write it out for you. And you'll see this in literature as LIMS. This is where, for whatever reason, and it's poorly understood, your immune system just thinks it's a good idea to start attacking the voltage-sensitive sodium channel, voltage-sensitive potassium, excuse me, I'll get it right, voltage-sensitive calcium channels. So you have an immune response to voltage-sensitive calcium channels. Well, that's a problem, because if your immune system is interfering with these voltage-sensitive calcium channels, can you not see how it is going to greatly affect synaptic release of neurotransmitters? Because if I don't have enough calcium coming in, I'm going to be greatly reducing the amount of neurotransmitter being released, because the amount of neurotransmitter being released is very much tied to the amount of calcium going into that presynaptic terminal. So this seems to be more specific towards the voltage-sensitive calcium channels associated with the neuromuscular junction. Again, I've said this before, I'll say it again, there are many, many types of voltage-sensitive calcium channels. So this particular syndrome here tends to be geared towards the ones associated with neuromuscular junction. So what will happen then is it's going to cause weakness of muscles, and typically it's going to end up involving upper extremity and lower extremity. That's where you're going to see it. Now, again, this is not fully understood. We do know that this LIMS, or Lambert-Eaton myasthenic syndrome, is very much associated with small cell lung cancer. Okay, we've already talked about small cell lung cancer. Small cell lung cancer. So what does small cell lung cancer have to do with that? Well, cancer and your immune system have a lot of interplay, and cancer can cause your immune system to do all kinds of things that it would not do if you didn't have cancer. And again, the biology is poorly understood on this, but there's something about small cell lung cancer, and what it does to your immune system is that there's a relatively high instances of LIMS with patients that are struggling with small cell lung cancer. Again, not sure why, but if somebody has this cancer, LIMS is something you're going to want to watch out for. Now, having said that, I'm not one to suggest that the only way you can have Lambert-Eaton myasthenic syndrome is with small cell lung cancer, or if you have that, you have small cell lung cancer, because about half of the LIMS has nothing to do with small cell lung cancer. But there's enough correlation between the small cell lung cancer and LIMS that it's something you clinically would want to be aware of. Again, it's poorly understood, as all immunocompromised types of, not immunocompromised, autoimmune is what I'm trying to say, autoimmune issues. Again, the mechanisms there are just completely not worked out at all. But we do know that some cancer is associated with this, but we also know you can get it without having cancer at all. But my take-home point on that is I'm just driving home a clinical point that involving something with these voltage-sensitive calcium channels. You start messing with those, then you're going to be altering the amount of neurotransmitter being released, and then there you go. Okay, so we'll end that here and pick up next time. I want to consider the end-plate potential. We will call this an EPP. The end-plate potential, as the name implies, is going to be the potential change on a postsynaptic membrane. So we're talking about a postsynaptic membrane. So that when a neurotransmitter binds to the receptor, you're going to get a change in the end-plate potential. And so if we're looking here, again, this is voltage. So there's my end-plate potential there. And I talked about this last time, that this is going to be a graded potential. And a graded potential is like having a light dimmer. It could have been this, it could have been that, it could have been that. You get all kinds. And again, the whole point is to bring it to threshold. So if I bring it to threshold, and again, for the 100th time, bringing it to threshold means I'm starting to open up voltage-sensitive sodium channels. So then and only then would I have an action potential. So there is my action potential there. Again, tied to voltage-sensitive sodium channels. So this is what's happening at the end plate or at the postsynaptic membrane. Now, if you are at a distance, in this case here, it's like, okay, 2 millimeters from the end plate. And so probably talking about maybe a muscle fiber. So 2 millimeters from the end plate, maybe you're down, down an axon or something like that. This would be the configuration of an action potential here, and there you just have a pure action potential. Then you say, well, what happened to the graded potential? Well, no graded potential here, so no graded potential here, because all I'm dealing with here are voltage-sensitive sodium channels. So the graded potential has to do with the receptor interaction with the neurotransmitter, all trying to get those voltage-sensitive sodium channels to open up to get the dominoes falling. So if I'm away from the end plate, there's no graded potential here. It's just basically just a series of voltage-sensitive sodium channels giving me that action potential. So that's what that's all about. So that's kind of an important concept we'll want to keep in mind. So now, because we're talking about a neuromuscular junction here, so got an end plate of a muscle fiber. What happens in reality is that this big old synapse here, okay, and I've got my acetylcholine sitting there, got my muscle fiber here, this is going to be my postsynaptic, and this is going to be my skeletal muscle fiber here. Fact of the matter is, as I said before, you have an action potential down there. It's going to release a large amount of acetylcholine, and one action potential down a motor neuron is enough to cause an action potential in the muscle fiber itself. Now, that is not true if you're talking neuron to neuron. Okay, so one synapse cannot light off an action potential in the downstream neuron because it's just too small. But if we're talking about motor end plate, they're huge. Yes, you can. So in between action potentials, suppose you had no action potential coming down here, then therefore theoretically say, okay, well then no neurotransmitters being released, and that's not true. Actually what happens is that this presynaptic terminal here dribbles acetylcholine. In other words, it leaks. So what you're going to have is you're going to have an occasional synaptic vesicle fusing with that membrane, not because of an action potential in the motor neuron, it just fused for whatever reason. So it is always dumping little small quantities of acetylcholine, and so what you get are going to be what is called miniature end plate potentials, MEPPs. miniature in-plate potentials, MEPPs. And so this is, again, voltage we're measuring here at skeletal muscle fiber at end plate. And so you have that, you have that, you have that. Those are not those are not action potentials. These are just little graded potentials. And so every time you see a little spike there, what you have is you just have a leak of an occasional synaptic vesicle. So none of these are action potentials. It's just a series of graded potentials. It's just noise. So no action potential here. That's not what we're talking about. It's all graded, and it's just due to the leaking nature of the presynaptic terminal of a motor end plate. So these are called, again, miniature end plate potentials. One quantum of acetylcholine in one vesicle can cause 1 MEPP. And it will induce about a half a millivolt change. So you get the scale here. So we're talking 0.5 millivolt change maybe from there to there. Okay, way different than obviously a full-blown action potential where you're going from, minus 90 or minus 70 all the way up to plus 60. So that's what we're dealing with here. And I think here, this is actually from here to here is maybe 3.6 millivolts. So it gives you a sense of scale. So this is basically background noise. Okay? All right, so I want to change subjects a little bit and talk just a few minutes on some deleterious molecules or pathology regarding the nicotinic acetylcholine receptors. And again, certainly not exhaustive. I'm just trying to toss your way some samples of how things can go sideways. So first up would be alpha neurotoxins. Alpha neurotoxins will bind to acetylcholine receptors and will lock them down. In other words, they'll block their opening. So if you have alpha neurotoxins locking down my nicotinic acetylcholine receptors, then acetylcholine has no effect on it. You therefore have knocked out the possibility of having action potentials in the skeletal muscle fiber, and basically you render that fiber to be inoperative. Common place you'll find alpha neurotoxins is going to be in snake venom, and here we're talking about cobra venom. Venoms in snakes are all different. The proteins in snake venom in terms of their deleterious effect, it kind of falls into two buckets. One would be the neurotoxin side of things, and the other would be the hemotoxin side of things. If venom is dominantly hemotoxic, then what that means is that the proteins that are contained in the venom are going to destroy blood cells and going to destroy tissue around the site of injection. So examples of that would be pit viper venom. Pit viper venom is dominantly hemotoxic. So pit vipers are going to be your rattlesnakes, your water moccasins, and your copperheads. And even then you have varying degrees of toxicity. Rattlesnakes are the most potent venom, again, dominantly hemotoxic. If you get bit by a rattlesnakes can make you dead. On the other end, you have copperheads. Copperheads are not nearly, their venom is not nearly as potent as a rattlesnake. So if you get bit by a copperhead, highly unlikely you're going to die from it. You may wish you were dead because you're going to get really sick and it's going to be very painful, but it's unlikely that you're going to die from it. And then the water moccasin is kind of somewhere in between. So you have the pit vipers. And then you have the snakes that are more neurotoxin oriented, and that would be like your coral snakes or your cobras. Their venom is primarily neurotoxin, so they're loaded with alpha toxins, and so how they're going to work is a snake will bite their prey, and it will paralyze them, eventually killing them, but certainly will paralyze them, allowing then the snake to pounce in to have its dinner. So that's how that works. One kind of interesting thing about cobras is that in areas of the world where you have cobras, cobras do have natural predators, and one's a mongoose. And so a cobra and a mongoose can square off, and usually the mongoose is going to win. Not because the mongoose is that much more quick than the striking velocity of a cobra, but that through a series of evolutionary changes, the mongoose, when they're born, already have a ready-made immune system to attack the neurotoxins from a cobra venom. So a cobra can bite a mongoose and is going to make any effect on them because their immune system has already been evolved to lock down any alpha toxins coming into their system. So that means that renders the cobra venom useless for a mongoose, and the mongoose will then eat cobras. So that's how that works. Curare, that is made from plants and barks of plants and such. You'll find these plants in South America, and the indigenous peoples of South America have long used curare to poison the tips of their darts and their spears. It also locks down nicotinic acetylcholine receptors in a similar fashion as the alpha neurotoxins do. So if you're hunting and you impale your prey, which is hopefully going to be your dinner, usually a spear isn't going to kill the prey right off, but if you cover or coat your tip of your spear with this curare, then it will partially paralyze or weaken the muscle activity of the prey, allowing you then to pursue it and to go in for perhaps the final kill. And then you always say, well, what happens if you eat it? And the curare degrades very quickly. By the time you cook the meat, it's no big deal, completely safe to eat. So curare is, again, something that you can do that would block the nicotinic acetylcholine receptors and therefore function as a paralytic. Another thing would be nerve gas. Sarin would be a type of nerve gas. The way nerve gas works is that it will inactivate acetylcholine esterases. So you'll recall earlier I said the way you control acetylcholine is by relying on the activity of the esterase to do it. Well, if you have an agent that blocks the acetylcholine esterases, then what you have is you have a situation where now you have no way of controlling the acetylcholine, and so it overstimulates the motor implates. It also is going to be having an effect throughout the central nervous system, so anywhere you have a nicotinic receptor, whether it be associated with muscles or be associated with your central nervous system, and you have plenty of nicotinic receptors there as well, that is going to cause a lot of problems in your central nervous system, in addition to the muscle paralysis. It's a very nasty drug, for sure, and a very terrible way of dying, but that's basically how that works. By the way, let me just say one other thing about another drug, atropine. Atropine is actually it is an antagonist to acetylcholine, nicotinic acetylcholine receptors. So one way of addressing anything that would overstimulate something like the sarin nerve gas, the atropine could actually help with that because, again, it's going to be blocking the activity of the acetylcholine as it binds to receptors. So that's just kind of a side point. So it could be used to kind of help with that. Atropine blocks other things too. Not only does it block nicotinic receptors, it's also going to be blocking non-nicotinic receptors or metabotropic receptors or muscarinic receptors. And I'll talk more about that a little bit later in terms of the various types of receptors. Let's see. Another one would be the toxin released from the bacterium Clostridium botulinum. That Botox is what we're talking about here. So I'll go Botox. This is mostly, it's mostly going to be associated with food poisoning, botulism. So what happens there? Well, this particular bacterium thrives in anaerobic conditions. In other words, low oxygen levels. And so this bacterium is in soils, it's in dust, it's around. And so back in the day, maybe you're canning something, you're cooking fruit or something, and you're wanting to seal it and maybe preserve it for the winter or something like that. So what can happen is if it contaminates the food stuff and you seal it off, now you're creating an anaerobic or low oxygen environment, and you're then allowing this bacterium to proliferate and crank out all these toxins while it's on your shelf, waiting to be eaten at a later time. You pop it open, you eat it, and now you've ingested all this stuff, and now it's going to be creating all kinds of problems. Could kill you, makes you very sick. So that's a problem with food poisoning because of the anaerobic conditions. So it's something you have to always be concerned about for sure. The Botox also can be used in cosmetics to alleviate wrinkles because it's going to relax the skeletal muscles under the skin. Originally, the Botox was used as a way of weakening muscles, extraocular muscles. So individuals would have an eye that would deviate one direction or another direction because of unequal tension on extraocular muscles moving the eye in the orbit. And so physicians would inject one of those muscles to weaken them to realign the eye. And that was kind of the first use, I believe, of Botox in a clinical setting. So they did that there, and then it was eventually discovered, hey, this also makes wrinkles go away around the eyes. And so a billion-dollar industry was actually born there. Botox can also be used to create muscle movement or to alleviate muscle movement disorders. And so if you have a patient that has abnormal contraction of a muscle group, you can actually go in and hit it with Botox, and it will weaken that muscle group and helps with that. The Botox is only temporary. It lasts maybe 3 months, and you have to go in and re-inject the Botox. So it can be used cosmetically, or it can be used to address muscle contractions that you don't want. One last thing, and not sure why this is, but injection of Botox in certain areas of the face can help some types of migraines. Again, mechanism not understood. But for some migraines, for some people, the Botox will actually help them with that. One other thing before we kind of finish up the deleterious part of this is going to be myasthenia gravis. I'm sure you've heard of that. That is another autoimmune disease. Again, mechanism not clearly understood, but it is where your antibodies, your immune system decides it's going to be attacking the acetylcholine receptors. And again, you can obviously see if you're having that, it's going to cause muscle weakness, of course. Now, interestingly enough, what happens is that the antibodies do more than just attack the receptors. They start destroying that postsynaptic membrane on the motor end plate. So they'll literally, because with the antibodies, these are IgGs, the antibodies will attack them, but then they bring in other molecules associated with the immune system, and it'll start destroying that membrane. It literally will tear out the nicotinic acetylcholine receptors. You'll actually have nicotinic acetylcholine receptors floating around in the synaptic cleft because they've been torn out of the membrane. And so you'll actually have a reduction in the nicotinic acetylcholine receptors at a motor end plate if we're talking this particular pathology, the myasthenia gravis. Also, as a part of destroying that postsynaptic membrane, or at least compromising it, is it's going to be tearing out voltage-sensitive sodium channels as well. So if you have lower than normal voltage-sensitive sodium channels and you're having lower than normal nicotinic acetylcholine receptors, then you can understand why you're going to have muscle weakness. Before I close this down, something else came into my head. It's kind of return back to the snake venom here for just a second. If you get bit by a snake, say, rattlesnake or copperhead, then one of the ways to address that is you're going to give the patient some anti-venom. And the anti-venom is given via IV. And the anti-venom is basically antibodies raised against whatever venom you're talking about. And so if it's the venom of a pit viper, then that's what you're going to get. Typically, these anti-venom concoctions, and it's a cocktail again of immuno proteins, are going to be made in either horse or sheep, polyclonal. So what can happen, though, is you, again, have the venom in you. You're going to be given an IV of the anti-venom, and so those sets of molecules or sets of proteins are going to be locking down the venom, and they literally can save your life. All well and good. The thing about it, though, is that you can be given the anti-venom once. Because if you come back the next year and get hit with another snake bite, you can't be given the anti-venom again. The reason is that you're going to have a reaction against the anti-venom, because the anti-venom are immunoglobulins that are from another species. You're going to have an immune buildup towards that, so that if I were to give you anti-venom today, okay, you're fine. But then if I wait 6 months, now your immune system is tuned to attack the anti-venom. So that's why you really only have one shot at an anti-venom. It's not good after you've had it one time, because now your immune system is going to fight that. So that's a real challenge. It's something you need to be aware of. The other thing, too, is that the anti-venom, because it is so labor-intensive to generate, because you're having to rely on other animals to generate these antibodies, is incredibly, incredibly expensive. So a typical regimen of an anti-venom in response to a snake bite can run you $30,000, $40,000, $50,000. I mean, they're crazy, crazy expensive. So if you don't die from the snake bite, you can die from the medical bill. Hopefully you have some good insurance that will cover it, but it's extremely, extremely expensive. And again, it's just good for one pop. After that, you really can't be given the anti-venom again. Okay, so we will end this here. We'll pick up on more considerations of synapses between neurons next time. Synapses can be between a motor neuron and muscle fiber, or it can be between two neurons. So I want to elaborate on that a little bit, because you have all kinds of variations in terms of how one neuron can talk to another neuron. We see here a basic structure of a neuron. We see there's a soma there. And again, that's the cell body, and that contains all the Golgi and all the other machinery of the neuron itself. Then we have a dendrite, and dendrites can have all kinds of shapes and elaborations. You can have some that are a little, like this, or maybe there's some that are even more branchy like that. So they come in various shapes, but all of these are considered dendrites. On dendrites, you also have things called dendritic spines. And so a dendritic spine, it looks like a little bleb or a little dot right there. Okay, these are dendritic spines. The reason that they're there is to increase the surface area of the dendrite itself. Now, what they have here on there, that's supposed to be a spine that looks totally unrealistic, because they're not that big. They just look like little bumps on there, but that's magnified for a purpose, but I'll get back to that in a second. And of course, then you have your axon, and then, of course, down here, could be, again, your presynaptic terminal. Okay? So what we have is that other neurons can come in and synapse onto a downstream neuron in many different places on that neuron. So you have here, and they've left part of it out, but I'll just kind of do that there. So I got a neuron there, and then, okay, maybe a neuron there. And this one's coming in and actually making synapses on the soma itself. So that's one scheme on that, and that would be called an axosomatic synapse. I think the name pretty much tells you what that means. Then you also have neurons, there, and maybe one here, coming in, and they're synapsing onto the dendrite itself, and that would be the axodendritic synapse. Again, name very descriptive. Now you can have a synapse onto one of these main branches here, which is what this symbolizes here, or you can have a synapse on a spine, these little dots right there you see, and so you have that. So that's another scheme. And then the final one would be that you have just a neuron here, neuron coming in, and it is actually making a synaptic connection on a presynaptic terminal. And so again, a lot of these terms are relative. So this would be a presynaptic terminal. Okay, and it is making a connection with some other, say another neuron here, you say. Okay, but what we have here is also a presynaptic terminal. From another neuron, and so I have a presynaptic terminal synapsing on a presynaptic terminal. But in the case of this situation here, okay, this, I'll just change colors for just for kicks, this is considered the postsynaptic membrane relative to this presynaptic terminal. So this is a postsynaptic membrane, and it is still a presynaptic terminal relative to this neuron here. So this is actually a very important scheme to understand, that many of your synapses in the central nervous system are connecting with another presynaptic terminal. So what's happening here is that this terminal here, this presynaptic terminal here, is affecting what's going on with the release of the neurotransmitter from that presynaptic terminal. We have spoken before about how neurotransmitters can be either excitatory or inhibitory. They can either encourage whatever's going on downstream neuron, or it can inhibit the downstream neuron. So you can imagine, and we're going to return to this in a moment, but you can imagine this presynaptic terminal here. Suppose that one there, we just change colors up just a little bit. Okay, so that one there, suppose it is excitatory. Okay, and suppose it's going to excite this neuron down here in some measure. And so it's doing so, again, by releasing neurotransmitters that are excitatory. But you have this one here, and suppose it is inhibitory. Just suppose. Okay, suppose that were inhibitory. So this one is trying to keep this one from releasing the excitatory neurotransmitter. So if I'm having lots of signal, lots of action potentials coming down this axon, that is going to inhibit this release of neurotransmitter that happen to be excitatory, which will then, of course, cause a downstream effect of that neuron there being less excited, because I'm dialing back the excitatory signal. But I'm doing it with another synapse on a synapse, or another presynaptic terminal synapsing on another presynaptic terminal. So you can see here you have all kind of combinations, and we're going to talk about that in a moment. Anyway, so those are the kind of the basic ways that an incoming neuron can talk to another neuron, either on the soma or on the dendrite or dendritic spine, or you have a presynaptic terminal synapsing on a presynaptic terminal. Another scheme that we have is we have two ideas called convergence and divergence. Convergence means that you're having multiple neurons talking to one neuron, and so that's a convergence of signaling. And so what you have here, one neuron receives multiple inputs from many neurons, which is always the case. Typically in the central nervous system, one neuron can be receiving thousands of inputs from other neurons. So it would not be uncommon for a neuron to have 5,000, 10,000 synapses coming on it, you see. So this would be convergence. Then you have also divergence, which is where you have one neuron talking to many other neurons. And again, that happens all the time in the central nervous system. There are situations, there are examples of neurons in the central nervous system where one neuron will make connections with hundreds of thousands of other neurons. Not all of them do that, but some do. So that gives you a sense of how broad a reach one neuron can have. So this idea that you have a neuron, a single axon, and then talking to another neuron, when you could literally have just thousands and thousands and thousands of these things coming out, talking to many, many, many other neurons. So the fact of the matter is in the central nervous system, you have both convergence and divergence occurring simultaneously, which gives you then a sense of how complex the connectivity is within the central nervous system. Something I may have mentioned already before, but I want to revisit this, is that unlike where you had a motor neuron talking to a muscle fiber, and that motor end plate is huge, releasing copious amounts of acetylcholine binding to nicotinic receptors, effecting an action potential throughout the muscle fiber. And all it takes is one action potential down that motor neuron, and that will cause an action potential in the motor fiber. When we're talking neuron to neuron, that is way not the case. One synapse does not cause in and of itself an action potential in another neuron. It takes a lot of signal to do so. So let's just take a look at this and see how this is working. So here's a cartoon. Either cartoon would have worked fine, but this one is non-myelinated, and that one is myelinated. You see the myelin sheath. It's the same principle either way. And so again, you have your soma, you have your dendrites and such. So you have all of these neurons coming in here, okay? And they're just making synapses everywhere, right? And so they're connecting. And so let's just say that green equals excitatory. So all of these now are releasing excitatory neurotransmitters, and so therefore they are causing EPSPs. Okay, so this again, it's a graded potential. So we're talking a light dimmer now, because again, I remind you that the cell membrane, of a neuron itself, okay, all that through there, okay, that is not an excitable membrane. In other words, it cannot have an action potential. It doesn't have the correct configuration of voltage-sensitive channels to have an action potential. The first part of the neuron that can actually have an action potential is going to be the very beginning initial segment of the axon, this guy right there, and that is called the axon hillock. So if this neuron here is going to have an action potential, it will start at the axon hillock and then will just propagate in that direction there. So the point of the input, all the thousands of input into this neuron, is to try to bring the axon hillock to threshold. If it can bring it to threshold, then it will have an action potential. So the reason that one synapse cannot in and of itself bring this axon hillock to the threshold. Well, first of all, it's too small. I mean, again, it's just infinitesimally small, and you're having an infinitesimally amount of neurotransmitter being released. I mean, many orders smaller than the amount of acetylcholine released on a motor end plate. But what it can do is it can depolarize by graded potential, causing EPSPs in that location there. And then we're also going to go back to the concept of length constant, where you have a depolarizing event on a cell membrane, and then it's going to have an effect downstream as you get farther away, but the effect is going to be less, diminished. So if I'm going to want this axon hillock here to be brought to threshold, I have to have a lot of excitatory inputs coming in here pretty much at the same time, and then collectively, all of that is enough to bring this to threshold. But I need all of it because, again, the length constant, again, I got fall off. You know, I might have a graded potential there, but as I get farther away, it's less and less and less. But when you put everything together, that's enough to bring that to threshold possibly. Now, here's another confounding factor, though, because as we said, you have many, many synapses in the central nervous system that are not excitatory, but rather inhibitory. So any particular neuron will go green is going to be excitatory. I'm also going to literally have thousands of neurons coming in and go red, okay, equals inhibitory. So all of those are going to be causing IPSPs. So they're trying to hyperpolarize the membrane. And so you could have IPSPs and EPSPs coming in at the same time. So what you have in this neuron is this massive tug-of-war from all the thousands of other neurons coming into it in terms of whether or not this one axon hillock is going to be brought to threshold or not. And this is how your central nervous system works. You have thousands of inputs of inhibitory, thousands of inputs of excitatory, and then what direction this is going to go in terms of will I be bringing this to threshold, and what will be the frequency I will be bringing it to threshold is going to be a function of the total strength of the inhibitory input and the strength of the excitatory input into this one neuron. And that's how it works. So I say here, one synapse, whether it's excitatory, inhibitory, may move the postsynaptic potential maybe anywhere from 0.5 to 2 millivolts. Again, that's not enough to do anything. But when you add it all together, then you might have an effect in terms of the axon hillock being brought to threshold or not brought to threshold. Okay, and so we can further illustrate this. And the down here, again, it's just saying the same thing with myelin. See these little guys there? Those are just symbolizing neuronal inputs. Okay, so I talked about EPSPs. So again, let me elaborate on that a little bit. Okay, an EPSP, excitatory postsynaptic potential. Again, this is a graded potential. It's a light dimmer. Okay, this is unlike an action potential, okay? This is not an action potential. Again, this is a non-excitable membrane that we're talking about here. So if I have an excitatory input brought in, I can measure my EPSP, and I'm maybe releasing, excitatory neurotransmitters, and it might bring the membrane from here to here, so that might be my EPSP. And then it falls off because maybe the neurons are stopping releasing neurotransmitters, and it goes back to baseline. So that's what that is. And again, when the neurotransmitter binds to a receptor, if the receptor is a channel, these channels open up just 1 to milliseconds, and then it ends, of course. Again, the flip side of that is if you have an inhibitory. Again, it's the mirror of this. That's an IPSP, again, graded potential, except it's going down in the opposite direction. So, again, both of these can be going on at the same time. Now, if we're talking about IPSPs, then we're talking about opening up chloride channels, opening up potassium channels here. And you'll recall that the nurse value for potassium is usually well below resting membrane potential, so that tends to hyperpolarize. The chloride channels probably tend not to hyperpolarize simply because of their Nernst value. So if you open up a chloride, remember you got you got a membrane here. I got lots of chloride here, a little bit of chloride here, and if I have a channel here, and if the membrane is sitting at minus 70, if the Nernst value for chloride is minus 65 or something like that, then you're not going to have chloride rushing in. Now, again, the chloride Nernst value can be altered, of course, by changing the concentration gradient, but just opening chloride channels is not going to lead to hyperpolarization, but it still will have an inhibitory effect. Why? Because if you're having an input, say, let's just go a different color here, and let's get back there. Come on. Blue. Okay. So suppose now I have a sodium channel here. Okay, a receptor binds. So suppose you have a depolarization. And so now I'm having sodium rushing in, and it's wanting to drive the membrane towards that plus 60 millivolts, because that's about where the Nernst value is for that. Well, suppose at the same time I'm having a chloride channel open up. Well, the chloride's rushing in, so what will happen is if chloride is rushing in, then it is going to keep the membrane from being as depolarized with the increase in the sodium. In fact, if I have one chloride rushing in relative to one sodium, then that's a net of nothing, right? Because I'm not altering the potential because I'm having one negative come in, I'm having one positive come in. So in the situations where you're talking about chloride rushing in is going to tap down the EPSP if they're happening simultaneously, which oftentimes they do. Okay? So this would be a type of inhibition. So you can inhibit by either opening up potassium channels or chloride channels. They just kind of have a little different approach to it. The chloride will rush in if the membrane is more positive than its Nernst value, and its Nernst value just a little bit beyond what resting membrane potential is. So it can be a very effective inhibitory as well. So inhibition, again, usually involves opening chloride channels or could be potassium channels as well. I'm going to talk about this a little bit later, but GABA is an inhibitory neurotransmitter, and it's going to be attaching or docking with a GABA A receptor. Okay, that's going to be an inotropic receptor there, and I'm going to talk about that in a minute. Right? And so, again, chloride will be rushing in there. But you can have, again, either GABA working with chloride, or you can have other transmitters, neurotransmitters that would be inhibitory as well, and that could involve opening up potassium channels. So this is a little bit of an elaboration on what I spoke of earlier in terms of how all these combos work together. So again, let's just spend some time. And this is basically a point of logic. So let's kind of walk it through and see if we are understanding things correctly here. So I got inhibition. Now again, inhibition is where I'm keeping that downstream neuron from going to threshold. I'm trying to keep it from having an action potential, the downstream one. So what I'm having here is inhibition. So over here, excitation. Okay, I'm going to have again some excitatory input. I'm going to have my EPSP. Okay, so that's pretty clear. And then if I'm inhibitory, then I'm going to have my IPSP. Again, these are both graded. If I'm having them both coming in at the same time, and suppose that the excitatory was just a little bit more intense than inhibitory, I could still have an EPSP, but it's not going to be as great. So again, I could have all these combos. I'm not saying that all the time that the excitatory is going to be more than inhibitory, because I could have also said, okay, let's let the inhibitory be a little bit more than excitatory, and then I could have had this, just a little bit. I'd have a real small IPSP. So again, this is all graded. This is all just a matter of whatever. And of course, if they're coming at the same time, they could cancel each other out and have no movement at all in terms of the postsynaptic potential. So you got all kinds of variations here, you see. And like I said, all this is going on at the same time. So looking at our synapse, our presynaptic terminal synapsing on a presynaptic terminal. So what we have here is, okay, here is my postsynaptic terminal, and since it's going up, so this is, and this could be another neuron, okay, right there. Okay, so it is being excited, hence the EPSP. So this is excitatory right here. So I got an excitatory neuron coming here, releasing all of its little excitatories, and it's causing an EPSP. Now, suppose that I were to have a inhibitory neuron coming in, and the inhibitory neuron there has inhibitory neurotransmitters, and let's just suppose they're GABA. Okay, so I got GABA, and I've got little GABA A receptors here. So I got GABA A receptors, okay, sitting on that presynaptic terminal. Okay, now just to keep things clear and honest, okay, I've got my little receptors here, whatever they are, binding to the excitatory neurotransmitters, but now I'm releasing GABA onto this presynaptic terminal. So presynaptic terminals have receptors for neurotransmitters as well, you see. So what can happen is, okay, I'm now, in this scenario here, the GABA is not being released. But on this one over here, now I'm having action potentials coming down. It's releasing GABA. Okay, and the GABA is binding to GABA A receptors. And therefore, in this situation here, if it's a GABA A receptor, that means it is going to be allowing chloride to come in. So note what happens here. And that is, I'm having an action potential coming down here. Okay, and as we know, action potential is going to be going through the presynaptic terminal. And then what else do we have here that's causing the release of neurotransmitter from the presynaptic terminal? Well, I have my voltage-sensitive calcium channels. So as the action potential is coming down, it is going to be causing those voltage-sensitive calcium channels to open up. And when they open up, calcium rushes in. And when calcium rushes in, I am now going to have release of neurotransmitter from here to here, you see. So the amount of neurotransmitter being released is directly dependent on the amount of calcium coming into that presynaptic terminal. The more calcium comes in, the more neurotransmitters are released. The less calcium comes in, the less calcium neurotransmitters are being released. So I have an action potential coming in, causing those voltage-sensitive calcium channels to open up, and there they are there, calcium just rushing in, causing that release of neurotransmitter. So I'm having an action potential coming down here, but what's happening with this action potential here is I'm having an inhibitory at the same time as this action potential is coming down here, you see. So now what I'm having is this action potential here is wanting to really depolarize the presynaptic terminal, opening up lots and lots of voltage-sensitive calcium channels, but I am having an inhibitory input at the same time. So therefore, this membrane here is not being allowed to depolarize to the degree it would want to be, because, yeah, I have sodium rushing in because of the voltage-sensitive sodium channels, but I'm also having chloride rushing in through those GABA A channels as well. So that causes less depolarization of this presynaptic terminal here. Therefore, less depolarization means less calcium coming in, and less calcium coming in means I'm having less neurotransmitter being released. Less neurotransmitter being released means I'm having a smaller EPSP on this neuron that's downstream. You see how you get the interplay there? It's just logic. Now, another thing that you'll note is that the action potential is coming down here. Look at the shape of the action potential here. What you have, remember I said a time ago, action potentials all or none, right? Well, I lied. Okay, here's a situation where I'm actually altering the shape of the action potential. And so where normally it would have that magnitude as a normal action potential, here it's less. Now, why did I make it less? Remember, say this is like plus 60 millivolts, okay, because that's the nurse value for sodium, right? But it didn't make it to 60 millivolts. Maybe it only made it to, 10 millivolts or something like that. Well, what happened? What knocked the top off of it? Well, the GABA. I got chloride rushing in. So that literally altered the shape of the action potential. So it is true that action potentials are all or none, except if you have something else coming in to influence the situation. And in this case, it is this inhibitory input that's doing that. Okay, I'll just point this out because there's one thing that really bugs me about this diagram here, and that is the shape here. It should be straight up, okay? There's no graded there. It should be straight up, and that should be straight up there as well. So we'll correct that because I don't like that piece of it. But that's a minor point. But you get the larger point of how something coming in can alter the potential change on this presynaptic terminal, which then is going to turn around and affect the amount of neurotransmitter being released. Now, I will tell you, you could have the same thing going on opposite. Okay, again, you can run the logic here and understand this. Suppose, and I'm not going to go through and repeat all this again, but suppose I had that coming in there, and then I have that coming in there. But suppose this was inhibitory. Suppose I was releasing GABA here. Okay? And suppose this was, so this is going to be inhibitory. Suppose this were to be stimulatory. Now what could happen if I have action potentials coming down here? You see, I'm exciting this here. That could actually end up causing more neurotransmitter being released because I am having a more powerful depolarization of this presynaptic terminal here because I'm releasing a stimulant onto this presynaptic terminal there, therefore causing even greater amounts of calcium coming in. Okay, you got all kind of combinations. So this one was negative, and this, let me see, hang on, let me go back. Let me go back here. Okay, so this one was this releasing positives, okay, but this was releasing negatives. This one's positive, okay, and this is negative, so I flipped, or I could have negative and negative, or I could have positive and positive. So you got all kind of combos. So it's just a matter of following the logic on this. Okay, I'm going to come back to this because this is a very important point to talk about. So I'm not done with this concept. I'm just trying to soften you up on this idea. So we'll end this for now, and then we'll pick up next time. So in this block here, I want to start off with a concept called summation. And summation has to do with how multiple synapses can interact with each other, or the release of neurotransmitters from multiple synapses can affect the postsynaptic membrane potential. So let's hook this cartoon up. Suppose I have a neuron here, and I have two neurons coming in. So this is going to be a neuron. It's going to be a neuron there. And so it's going to be neuron number 1 and neuron number 2. So we're going to key off this. Now, what would happen if I were to have a single action potential in 1? All right, and so a single action potential in one, single action potential coming down. What will the effect be on that postsynaptic membrane there? Well, it'll be this. So this is EPSP on the postsynaptic membrane. And where's my postsynaptic membrane? Right there. So if I have an action potential coming down, and assuming this is excitatory, okay, making that assumption here, I'll have a single EPSP here. Well, I've already wrote it down. EPSP. Right there. And again, a graded potential. Now suppose, and it takes a certain amount of time, right, from there to there. Now suppose I were to have, this is the second scenario over here, I were to have an action potential coming down, but right after that I have another action potential. Now again, with the timing, you can have almost 1,000 action potentials a second. So one of the controlling points in the central nervous system is frequency of action potential. You may have 5 action potentials coming down an axon per second, or could be 100, could be 500. Again, it just varies. So you have a frequency of action potential coming down, and suppose I were to have an action potential, and right after that, very close to it, maybe just a few milliseconds after that, another action potential. So the second action potential comes down before this thing is going to baseline. Because when you have an EPSP, EPSPs are kind of slow in the sense of you'll have a depolarization, and they just gradually come down. But suppose I have an action potential right there, or coming down the action potential from number 1, and then chasing it is another action potential that arrives before this EPSP goes to baseline. Well, what's going to happen is action potential 1 and then action potential 2. So you'll note that if I have another action potential coming down from neuron number 1 in rapid succession, I'm going to have a greater EPSP. Because I hit it, and before it went down, I hit it again, so you can cause it to climb. So I can now have a greater EPSP by having 2 action potentials in rapid succession down neuron 1. Therefore, I'm going to have a greater effect on that postsynaptic membrane there, which is what this is, of course. So this is called temporal summation. Okay, temporal summation. Because again, the postsynaptic terminal, the postsynaptic EPSP can last, 15 milliseconds. So 15 milliseconds, okay, from there to there. Well, in 15 milliseconds, you can have 10 action potentials coming in, right? Because the action potential is slightly over a millisecond, so I could have a number of them. So when you hit them in rapid succession, I can cause that EPSP to climb. It's called temporal summation. So let's go back to another scenario now, and suppose we had the following. We now have an action potential from number 1. Now we're also going to have an action potential from number 2. So again, this is over here. This is going to be the postsynaptic membrane here. Okay, so again, this is reading what's going on in the postsynaptic membrane. So now I have a single action potential coming down for 1. Okay, there's my EPSP. And then sometime later, I have an action potential coming from neuron 2. There's my EPSP there. Okay, so again, because this is a point of confusion, it says single action potential in 2. This is not the action potential. This is my EPSP. EPSP in my postsynaptic membrane. The action potential occurred up here or up here, okay? So this is my EPSP. So you have one here. So they're spaced apart, so you have an EPSP and then another EPSP. So the question is, what would happen if I had an action potential coming from here and here at the same time? If I had them coming at the same time, I'm going to get a larger EPSP in my postsynaptic membrane here. So you have a summative effect. So this is called spatial summation. Spatial summation means I'm having several from different neurons coming in, arriving at the same time, causing even a greater potential change towards the positive. So spatial summation and temporal summation. And I think you know where I'm going to go with this, which is they happen simultaneously. So I have both temporal summation and spatial summation coming in at the same time. These are not separate. Okay, this again, I could have variations in frequency, and I could have again them coming in. Now, this is with this example here. This is all excitatory. I could have said the same thing if these neuron number 1 and neuron number 2 were inhibitory, except I wouldn't be talking about EPSPs, I'd be talking about IPSPs. So I could have spatial summation and temporal summation for inhibitory. Therefore, I would have a greater IPSP. So I could have done it with that as well, but the principle is the same. Okay. So facilitation. Often summated postsynaptic potential is excitatory in nature, but has not risen high enough to reach the threshold for excitation. Now again, where is that threshold? It's going to be the axon hillock. So I'm trying to get that axon hillock to bring it to threshold so I can have an action potential downstream here. But what you have is a membrane is near to the threshold for firing, so just a few more excitatory inputs can induce an action potential. In other words, let's just use a little example here. Okay, we're assuming here that, let's see, the A and B, okay, this is excitatory, B is excitatory, C is going to be inhibitory. So here I'm having an action potential down A, and so there's my EPS. Now the EPSP, this is postsynaptic membrane, okay? So I'm measuring on that postsynaptic membrane on these. So I have a action potential on A will cause an EPSP. Another action potential on A, EPSP. Temporal summation, which we just talked about, now it's going higher. Spatial summation, okay, A and B happening at the same time, even higher. But if I'm having them both going on at the same time, both spatial and temporal, all of a sudden it can climb, it can climb, it can climb, it can climb. Boom, action potential, and mission accomplished. But again, this action potential occurred at axon hillock. Okay, so I'm having an effect in terms of EPSP, even on the axon hillock, but I got to bring it to threshold that if I do have a threshold and action potential, it will occur at the axon hillock. It won't be occurring there. The axon hillock is going to be down here. So again, just to be clear, I'm going to have a EPSP here, EPSP there. Well, if I have an EPSP there, that means I'm also going to be having an EPSP here as well. EPSP there. It won't be as much because it's farther away. But again, if I start putting all these synapses that are excitatory together, it's going to again cause greater EPSP on that hillock, which again could lead to an action potential. So again, this is facilitation. In other words, these guys are just helping each other out. Okay, so this is where I'm going to return to that concept that I talked about last time in terms of, again, following the logic. So here I have, well, let me go back because I left out something. I'm sorry. Just saw it here. Okay, because I left out poor OC over here. Okay, inhibitory. So if I'm having an inhibitory input here, that could be, that's my IPSP there, right? IPSP. Again, I'm going to have an IPSP there. We could also have an IPSP here because, again, the distance, it'll fade, but it'll still have some effect on the hillock. So there, I'm maybe opening up potassium channels, and I'm causing a hyperpolarization. But what would happen if I were to have, say, A and C at the same time? Well, they cancel each other out. I don't have I could cancel each other out. So then I don't have a EPSP or an IPSP. I just basically have a net nothing happens because they cancel each other out. So that's what that's all about. Okay, let's get back to this. Now we're going to focus on here. We're going to focus in. I'm going to revisit what I was talking about in terms of the amount of calcium determining how much neurotransmitter is being released in a presynaptic terminal. And I'm going to focus in on a synapse on a synapse. And again, the reason I'm kind of doing this is because there's a lot of this going on in the central nervous system. This happens all the time. So here I have the filled in. That is going to be inhibitory, and the open is going to be excitatory. So open here, filled in here, inhibitory, excitatory. Okay, so let's make some sense of this. So let's just suppose that I have, let's just suppose I'm having an action potential coming down neuron A, and it's going to try and have some effect on neuron B here. Okay, so let's get straight. What's what? Postsynaptic potential. So postsynaptic potential, that's going to be what I'm looking at right there. That's what I'm measuring. Whereas presynaptic, go here, the presynaptic, okay, I am measuring what is going on right there, okay? So I have an action potential coming down A. So what I'm having now is my presynaptic potential. There is my action potential in presynaptic A. So I have my action potential. Now note, I have my action potential, so this is going to be in millivolts here. So I'm changing that. That's my change in millivolts. Now, okay, now this is what I don't want you to be thrown on here. Okay, this right down here, the calcium, green. Okay, calcium, this scale here, this is not an IPSP. This scale here, I am measuring nanoamps, okay? I'm measuring flow of current. So this curve here, that's not voltage. I'm not measuring voltage change. I'm measuring the amount of calcium flowing in. And so so the more this goes down, the more flow of calcium there is. Now you say, well, why is it going down and going so it's going up? Well, this is a matter of convention in the sense of this would be negative nanoamps, and that's because I'm having a flow into the cell. If it was flowing out of the cell, calcium was, then it would be up like that. But it isn't, so that's just convention, so don't get thrown on that. My point is the larger that amplitude, the more calcium is flowing in to that presynaptic terminal. And remember, we have to have calcium flowing into that presynaptic terminal to release neurotransmitter from it. So you have the action potential here. That action potential is going to open up voltage-sensitive calcium channels, allowing calcium to come in. Therefore, that's where I'm getting my nanoamps from. So calcium is flowing. So calcium is flowing, which ends up causing the vesicles to fuse with the membrane, releasing their neurotransmitters, which we have defined as excitatory. Therefore, I'm going to have an EPSP on the postsynaptic membrane. So there you go. Now, suppose at the same time I'm having an action potential coming down neuron A, I'm having an action potential coming down neuron C. Now, neuron C is going to be releasing inhibitory neurotransmitters. Maybe it's releasing GABA. Okay, that's very common. GABA, okay, this type of connection here, GABA on a presynaptic terminal, very common. Okay, just another way of controlling neurotransmitter release. So if I'm having an action potential here, this is inhibitory, excitatory. So what's going to happen is that here is going to be my action potential, okay, action potential okay, in presynapse A. But note what happens. Note what happens here. Now my action potential, it's not as high as it was here. The amplitude is reduced. Why is the amplitude reduced? It's reduced because I am releasing inhibitory neurotransmitters binding to, in this case, GABA A receptors, allowing chloride to flow in as the membrane is trying to depolarize, and the flow of chloride caps off the amount or the amplitude of the action potential. This guy wants to go to a plus 60 because that's the Nernst value for sodium rushing in. But when it's trying to head up in that direction there, I've got chloride coming in, complements of the GABA, that keeps it from getting to plus 60. It'll go up. So maybe you're up here, and I'm going to make this up. Maybe this makes it to plus 10. Okay, it made it sort of up there. But at plus 10, I'm now far away from the Nernst value for chloride, so chloride's going to be rushing in. So it tops off or taps down the amplitude for that. Well, if I'm having a less of a depolarization, because it's only, say, going to plus 10, that means I'm having fewer voltage-sensitive calcium channels opening up. And if I have fewer voltage-sensitive calcium channels opening up, what's happening to the calcium flow? Look at that. Woo, right there. Okay, I'm inhibiting the flow of the calcium, and so my nanoamps is going to be less. And if I have less calcium flows in. Less calcium flows in means less excitatory neurotransmitter being released, which means I'm now having a smaller EPSP. So I have controlled now the amount of neurotransmitter by using an inhibitory onto an excitatory. So that's how that works. So let's go for another example. Let's change up. Again, you got all these combinations. So in this case, let's go, this is presynaptic inhibition, classic presynaptic inhibition. And again, most of the presynaptic inhibition in the nervous system is going to be complements of GABA binding to GABA A receptors. Okay, up over here. So what we have here is presynaptic facilitation. So now let's change the rules. So now we're going to say A is excitatory, boom, and we're going to say neuron C is excitatory too. So this part's the same, right? I mean, that's just like what we had up here. Okay? So, but look what happens now. Is that if I'm having an action potential here, okay, coming down there, and at the same time an action potential coming down here, so what's going to be different? Well, what's going to be different is going to be the shape of the action potential from neuron A. Okay, remember this is neuron A here, okay? So it's still going to go up to plus 60. Okay, still going to go up to plus 60. That's cool. But what happens is I'm going to change the shape of the depolarizing event. I'm going to make it broader. Why am I making it broader? Why am I causing that period of depolarization to last a longer period of time on this presynaptic terminal there? Because at the same time, I am releasing excitatory neurotransmitters onto it as well. So again, now I'm interfering with the system. I'm tipping the scale towards the positive. So that is going to cause the depolarizing membrane in this presynaptic membrane here to last longer because I am exciting the membrane that's being excited. In other words, I'm exciting it because of the action potential here, but I'm also exciting it because I'm releasing excitatory neurotransmitters from neuron C that will broaden that. And if I broaden that now, that is going to cause more potential. I'm going to have more calcium coming in. It's going to take a longer time for those voltage-sensitive calcium channels to close because I'm juicing the system by adding an excitatory input on the excitatory neuron, and that will result in a larger EPSP, EPSP, you see. So again, it's just a matter of just logic in terms of how you can configure this. So this is negative and positive. This is positive and positive. I mean, I'm not going to go through all this, but you could also have a negative and a negative, or you could have a positive and a negative. So you got 4 different scenarios here in terms of the facilitations. We've just done 2 of them, but you can use your imagination and do the others. Again, very, very important fundamental concepts here in terms of how all this works. And also it gives you a sense of how complex this system can be. All right. So kind of pulling some things together here. What you have is, now I'm looking at the post-synaptic membrane here. So in the postsynaptic membrane, including the hillock itself. So suppose that I'm having an incitatory input, I'm having inhibitory input. Now they're fighting it out, fighting it out, fighting it out. So what you have is that and this is actually true, the resting membrane potential of a neuron isn't so resting because it's always dancing around because it's always having input into it. It's not the case that a neuron is sitting in your central nervous system and nobody's talking to it. Somebody's always talking to it. Other neurons are always releasing either excitatory or inhibitory neurotransmitters. So the membrane potential, quote, resting or quote, resting, is just dancing around because I'm having this tug of war in terms of excitatory and inhibitory. But it could be at some point the excitatory is greater than the inhibitory, then I'm going to have my active potential at the axon hillock. And then it will become one of the active potentials going down, affecting some other neuron. Okay, so again, this is kind of a putting things together. Now, I do want to raise one interesting configuration that I haven't said anything about, but you actually have these. And this is called, it will be an autopsis. Autopsis. Autops, or autopsis, if it's plural. Okay, what's an autops? Like a synapse, except, well, what you have is you can have actually neurons. Okay, well, I didn't want that. That's weird. Delete, try it again, boom, boom, boom. Okay, and so it's going to go down and talk to another neuron, so forth, so on. But what you also have is a neuron can loop back around and talk to itself. Okay, that would be an autops. Okay, and so this is thought to play a role in self-regulation. I'm not going to pursue this too much on there. I won't pursue it at all, actually. I just want you to know they're out there. So not only can a neuron talk to other neurons, a neuron can talk to itself. And so it can either, if I have an increase in action potentials here, it could either be a negative feedback causing less action potentials, or it could be a positive feedback. It just depends. It depends on the nature of the receptor here. So again, this is kind of a way of having self-regulation. So autops, or autopses if it's plural. Okay, last point for this section, and this is nothing here that's new. I'm just kind of pulling everything together. Okay, so I have my voltage potential change here, and again, this is from some other experiment. So in this case, the change is up to plus 10. Yeah, I keep saying that a active potential could go to plus 60, and most of the time it does, but you have some cellular situations where it can be less than that, but don't get hung up on that. So here's an active potential going from minus 70 to plus 10. Again, the plus 10 doesn't make any difference. So this is going to be in my presynaptic. So I have that. So note now that as I'm having my action potential in the presynaptic cell, I'm also having an increase in calcium current because I'm opening up voltage-sensitive calcium channels allowing calcium to flow in, and here is my nanoamps, okay, so down to 400 Again, the negative simply means the direction of flow, so it really neither here nor there. So I'm having my action potential and the presynaptic terminals. This is presynaptic, and then my calcium current in the presynaptic membrane there. Now, what goes on in the postsynaptic membrane? This is my postsynaptic membrane there. So I'm going to have an EPSP. Okay, I'm assuming that the neurotransmitter being released is excitatory. So that's the assumption here. So assuming it is excitatory, I'm going to have an EPSP on the postsynaptic membrane. And again, let's just make this point because I want to make sure we're clear on this. Boom, boom, boom. Okay, so if I have a synapse coming in there, and suppose it's excitatory, I'm going to have an EPSP there, but I'm also going to be having an EPSP here too. EPSP too. Again, I mean, what happens here affects here, you see. Now, the EPSP here will be greater than the EPSP there, but still it's going to have some effect. Okay? So, I'm having my EPSP here or here, both actually. But if I bring the EPSP to threshold here, then and only then will I have an action potential at hillock. So that's basically all that's going on here. Presynaptic action potential, which is going to then open up voltage-sensitive calcium channels, allowing the presynaptic neurotransmitters to be released, and if they are in fact excitatory, that means I'm going to have an EPSP on the postsynaptic membrane, which could bring the axon hillock to threshold. And if you do, then you're going to have an action potential. All right, so that's hopefully been helpful for you. We'll see you next time. I want to zero in a little closer to what is actually going on with the vesicle and how the vesicle actually fuses with the membrane to release the neurotransmitters in the presynaptic terminal. So I'm just going to do a little cartoon here just to give us some context. Okay, so we have a presynaptic terminal here. All right, so then I'm having some vesicles here, and let's just say that the vesicle is filled with neurotransmitters. Now, where did those neurotransmitters come from? Most of the neurotransmitters are synthesized in the presynaptic terminal. So they are synthesized, and then a transporter is going to grab that one and put it into the vesicle. So each neurotransmitter is going to be paired with a transporter protein that is in the cell membrane of the vesicle, because the cell membrane of the vesicle is bilipid layer as well. We'll grab that neurotransmitter, fill that synaptic vesicle with neurotransmitter. So now they're full. So what exactly is going on in terms of how they fuse? This is a very active process. So this is not one of those deals where when it comes time to release neurotransmitters, that all of the vesicles just fuse with the neurotransmitters because they know that's what they're supposed to do. As we said earlier, the whole process is driven by calcium. So I have a lovely cartoon here that's going to help us out. So here is part of my presynaptic vesicle here, a synaptic vesicle. Okay, got neurotransmitters in here. Okay, and you see the bilayer there, so it's just a little piece of it, right? So what you have is that you have proteins that are associated with every presynaptic vesicle. So in general, we're going to call these V snares. Okay, the V stands for vesicle. And these are going to be a collection of proteins that are associated with the vesicle itself. And the two major ones is going to be synaptobrevin 2 and the synaptogin. Synaptotagmin. So synaptotagmin, synaptobrevin 2 are going to be two proteins associated with the vesicle. Let's find them down here. So the synaptotagmin is right there. So I'll just go, okay, there. Okay, all of that is the synaptotagmin. Okay, very complex protein. And note, it is bound, it is hooked into the cell membrane of the vesicle itself. Now, the synaptotagmin is the protein that interacts with the calcium. Oops, didn't mean to do that. There's calcium right there. Okay. So the calcium, when we say that voltage-sensitive channels opening up, allowing calcium into the presynaptic terminal, and then up to this point, magically the calcium causes the vesicles to fuse with the membrane, releasing their neurotransmitters. Well, here's where it's not magic. The calcium is going to interact with the synaptotagmin, and it will change its configurations. It's going to create a cascade of events. Okay, so that's step one, is that. So that's one of the V snares. The other V snare, and we'll go a different color here. Okay, synaptobrevin. Okay, synaptobrevin, and we'll go gray. How about that? Well, let's not do gray. Let's do some other color. Let's do obnoxious pink. Okay, so the synaptobrevin, which is right there, and so there it is right there. Okay, so you got that there. So those are my two proteins there. And so synaptobrevin is actually interplaying with some other proteins. So we got that guy right there. So that's my two V snares, or my major ones. Okay, another, if you get in the literature, another name for this is going to be VAMP. And VAMP means vesicle membrane associated proteins. Okay, so that's another phrase for some of these proteins, VAMP. Okay, that's just a side point. So I have that. Now let's go with my T snares. And so the major ones that I'm going to talk about here is going to be SNAP25 and syntaxin 1. So let's find another color here, and we'll go orange. So my syntaxin 1 is going to be right there. Okay, see him, syntaxin 1, all that is going to be syntaxin 1. Go ahead and syntaxin 1, it'll be that one there. And then the other one, we'll do a different color. We'll go greeno. Okay, green. Okay, that one there, that is going to be the SNAP25. And so the SNAP25 is this guy right here. Okay, so SNAP25 right there. So you get these four major proteins that interplay. So what's going to happen here is that when you have an abundance of calcium coming in and interacting with the synaptotagmin, that is going to, and this really doesn't, the picture doesn't really illustrate it, but you just have to use your imagination. It's going to cause the synaptotagmin to interact with these proteins here, and will cause a zipping action that will literally draw the vesicle and will cause it to fuse with this presynaptic membrane here, releasing its contents. So it's a very complex interplay with these major proteins, and I'm still calling them V snares and T snares, although you need to know the major names or the major proteins of the T snares and the V snares. The shorthand for this, for SNAP25, soluble, oops, back there, going to be soluble, that's going to be the S, and it's going to be N, N-ethylmalamide, N, well, it's not a good N, is it? N, and that's going to be where the N comes from, SNAP, ethyl, maleimide, activating, that's where the A comes in, protein. And that's where that comes in there. The snare, S-N-A-R-E, is going to be soluble. Here's the S-N, ethyl, maleimide. Sensitive factor activating protein. And so you got your S, N, A, R. Receptor, sorry. Receptor, S-N-A-P-R. So that's where you get your snare. The actual RE is going to be RE on the receptor side, and I guess I just want to make it cute. Anyway, so that's snare. It's going to be that. So you now want to know what SNAP stands for and snare stands for. This was pretty big stuff when scientists figured this out. Actually, they won a Nobel Prize for sorting out exactly how this actually works in terms of releasing neurotransmitters. Okay, so again, just kind of bigger picture here is that you have V snares and T. Oh, the T, sorry if I got mentioned that. The T snares is referring to transmembrane of this presynaptic terminal here. So this is the T and this is the V. This is just how they chose to name it. So T snares, V snares. You have an interaction of the T snares, V snares triggered by calcium coming in. And the protein that is going to be interacting with the calcium is going to be the synaptotagmin. And so the synaptotagmin, again, is one of the V snares. And you have these four, and there are more, but this is a simplified version that actually causes the zip, brings it down, and causes it to fuse. So that's what's going on. All this is driven when calcium rushes in. Okay, so we got that. So let's pick up another topic. And my other topic has to do with the receptors of neurotransmitters. Now, I've been talking about neurotransmitters for a while now, and I probably have mentioned this before, but the biological effect of a neurotransmitter is strictly dependent upon the receptor. If you let me design the receptor, I can make that neurotransmitter do anything I want. It's always all about the receptor. So you have a neurotransmitter, and the neurotransmitter could be excitatory or could be inhibitory. It depends upon the receptor it binds to, and there are numerous examples, and we'll talk about them later, where a neurotransmitter could be either one, depending upon what type of receptor is found on the postsynaptic membrane. So it's all about the receptor. So you have two general classes of receptors, and I've mentioned this before, but you have inotropic receptors. Inotropic receptors means that when the ligand, in this case neurotransmitter, binds to the receptor, it's functioning as a channel. So it's a receptor that is also a channel. So the ligand or the neurotransmitter binds to the receptor, and then that's going to change. Something about that receptor will change where it will either open or close, depending upon the receptor. So in many cases, a neurotransmitter binds to a receptor. If the receptor is inotropic, channel will open and allow electrolytes to go through. So in the case of nicotinic receptors, we saw that the acetylcholine binds to the nicotinic receptors. It opens and allows electrolytes to flow through. It could be calcium, mostly sodium, but also could be chloride. excuse me, potassium. So potassium, calcium, and sodium are the ones that can flow through a nicotinic receptor. We saw GABA. If a GABA A is an example of a inotropic receptor that's going to bind to GABA. GABA binds to it, opens it up, allowing chloride to possibly flow through. So all those are examples of inotropic receptors. Another type of receptor is going to be a metabotropic receptor. A metabotropic receptor are not functioning as ion channels. A metabotropic receptor going to bind to a neurotransmitter will bind to it, and it is going to be causing a change in the cell itself by way of second messenger systems. Now we're talking G proteins, IP3, DAG, etc. So many, many, many neurotransmitters are in fact metabotropic. A large percent of the receptors for neurotransmitters are not ion channels. They will bind and will cause some type of downstream biological effect in that postsynaptic cell itself. Now, many times what will happen is that that receptor that's metabotropic can in fact cause an EPSP or an IPSP. But it will cause that by opening up channels downstream through a series of biological activities. So I got some cartoons here to show you, and I think what we're going to do for this one is to go with two examples, and we're familiar with this. We have two types of acetylcholine receptors. We have nicotinic. We talked about this before, of course. Here's my nicotinic receptors. And then I have my muscarinic receptors. My muscarinic receptors are metabotropic. My nicotinic receptors are inotropic. So, just a little review here. So this would be an example of, say, a nicotinic receptor here. Nicotinic acetylcholine receptor. Boop, there. So I'm going to have some acetylcholine here, and again, remember, it takes two of them to open it up, so there's my two acetylcholines there. Opens up, and then it permits sodium to rush in, permits potassium to leave, and also, just kind of throw in here, also could allow calcium to come in. So that's basically a classic inotropic receptor. And so nicotinic acetylcholine binds, and again, because of the nernst value, most of the activity is going to be sodium flowing in, depolarizing the membrane. So we've been over that many, many times. So what's going to go on with a muscarinic receptor? Okay, it's metabotropic. So here we have, again, a neurotransmitter. We're just going to say this is acetylcholine. It's going to bind to receptor, and this is going to be muscarinic receptor, acetylcholine receptor. And again, it is a metabotropic, so it binds. So when it binds, now I've got a series of cell biology. You know, we're going to have all these ATP, cyclic AMP, protein kinase, you know, a lot of cell biology going on here. And so suppose, and in fact this is what happens, is that it's going to come in and maybe phosphorylate a channel over here. And maybe this channel is such that when nothing is happening, this channel is open to potassium, okay? So now this channel is contributing to the resting membrane of a potassium channel. So the channel is open. In that case here, it's going to be contributing to the resting membrane potential because it's going to be contributing to the permeability of the membrane for potassium. Now suppose that I have a acetylcholine bind to it, and as a result of, say, phosphorylation of this channel, it phosphorylates, and that means it's changing then the shape of the protein and closes it. So what that means is that now it is no longer permeable, permeable to potassium. And if it's not permeable to potassium, what effect is that going to have on the membrane potential? Well, it is going to cause an EPSP. I'm making the membrane less permeable to potassium, therefore potassium has less say-so in the resting membrane potential, And where does potassium want the membrane potential to be? Really, really negative. So if I start making the membrane less permeable to potassium, that's going to cause the membrane to be less negative. It's going to go up. It will cause an EPSP. So this would be an example of in this case, muscarinic receptor, acetylcholine binding to it, again, causing a potassium channel to close, causing an EPSP. So I'm getting EPSPs either way, either through the inotropic or metabotropic. It's just that the effect is, in fact, downstream. I've made this point before, but I just want to emphasize it. You have many types of receptors, even subtypes of receptors. So with my example that I'm talking about here with the metabotropic receptor for, like the muscarinics, there are many subtypes of this. You don't have to know this, but there's an M1, an M2, an M3, and an M4, and M5. And even you have subtypes of subtypes. So not all receptors, even though they're called, say, given a name, you have subtle variations throughout the central nervous system with this. So again, it gets a little complicated. So in this example here, the muscarinic, we talked about, it could cause an EPSP. The biological effect of receptors really, again, can be wide and varied depending upon what we're talking about. Acetylcholine on smooth muscles, some acetylcholine receptors, when acetylcholine binds to the receptor on a smooth muscle, will cause the smooth muscle to contract. There are other types of acetylcholine receptors, again, muscarinics, that when acetylcholine binds to them will cause the smooth muscle to relax. So again, I mean, it just depends upon the receptor as to what the effect is going to be. But again, if you're talking about metabotropic, it's all about all this cell biology that's kind of underneath the hood when it binds as well. So you could have, again, there are other examples that we may run into later, where you could have a metabotropic receptor and the neurotransmitter binds to it, and instead of causing EPSP, could cause an IPSP. It could be that it's working on a potassium channel that's normally closed, and then through second-messenger systems could open up the channel to potassium, therefore causing an IPSP. Again, it just depends upon what the cell biology of the downstream cell membrane is as to what the effect the neurotransmitter will have on it. But again, my larger point here is that you have two general kinds of receptors, inotropic, metabotropic. I used acetylcholine receptors as an example of showing you that one neurotransmitter could have both inotropic and metabotropic receptors. The fact of the matter is, again, the vast majority, I mean, all of the neurotransmitters have an array of varying types of subtypes of neurotransmitters, some receptors, some neurotransmitters, all of their receptors are metabotropic, but again, a wide variety of metabotropics could have different biological effects. Some neurotransmitters have an array of receptors that some are metabotropic, some are inotropic. Again, it's quite varied. So anyway, this is just kind of an example because I'm going to be referring to metabotropic versus inotropic in future presentations. I just want you to understand that concept. Okay, so we'll bring this to an end and we'll pick up next time. I just want to remind you, when it comes to neurotransmitters, we have neurotransmitters that are excitatory in nature. We have neurotransmitters that are inhibitory in nature. But the nature of the neurotransmitter is all about the receptor. And as I've said before, if you let me design the receptor, I can make a neurotransmitter do anything I want. So the activity, the effect of neurotransmitters on a downstream cell, whether it's a skeletal muscle or smooth muscle or another neuron or whatever, that it's going to be a function of the cell biology of the downstream cell, and it's going to certainly involve the receptor on which the neurotransmitter binds. Now let me make a more historical point. There is something in the literature called the Dale's principle. And Dale's principle basically says that one neuron will release only one neurotransmitter type. So if a neuron is dopaminergic, that means it's only going to be releasing dopamine. Or if it's GABAergic, it's only going to release GABA. Dale was a neuroscientist in the 20th century. He won a Nobel Prize. In fact, Dale was the one who worked out the activity in the cell biology of acetylcholine. Well, it turns out that Dale's principle is completely wrong. In fact, there are many, many instances where a neuron in the central nervous system can release multiple types of neurotransmitters at the same time. Also, in the regulatory environment of neurotransmitter release, there are other mechanisms such that the quantity of one type of neurotransmitter versus another type of neurotransmitter, both of which would be released from a neuron, can be regulated. There are situations where a neuron can release both an inhibitory neurotransmitter and an excitatory neurotransmitter at the same time. But there are regulatory effects that could tweak the release of that those sets of neurotransmitters from a neuron, where in one instance it may release more excitatory neurotransmitter, and at another time it may release more inhibitory neurotransmitter. So it gets rather complex. But you can imagine then if a neurotransmitter can release multiple neurotransmitters and that the level of those neurotransmitters released can be regulated by other cell factors, you can see how complex a system can be pretty quickly. So let's take a look at acetylcholine. We've talked about this before. You'll find acetylcholine in all motor axons arising from the spinal cord, and then also axons arising from the brainstem as well. You'll find them in the neuromuscular junction. So we have neurons that come from the spinal cord, and they'll innervate skeletal muscles in your body, but you also have nerves coming from the brain stem itself, and the brain stem can then synapse onto skeletal muscles such as your tongue or the muscles on your face and such. So if it's a motor neuron, then and again, the definition of a motor neuron is a neuron that is going to be synapsing onto a skeletal muscle. So regardless of whether the neurons come from spinal cord, whether they come from brainstem, if they're synapsing on a skeletal muscle, then they're considered a neuron. And so the neurotransmitter that they release is, of course, acetylcholine. You can find acetylcholine also in the autonomic nervous system. We've spoken of this before. So we know that if you have, for parasympathetics, you're going to have a neuron that's going to be living in the central nervous system. It is then going to leave the central nervous system and then will synapse onto another neuron that's going to be in the outside of the central nervous system. It will then give rise to an axon, and then it is going to be releasing neurotransmitter on whatever organ that is releasing on. So you have the neuron that's coming from the central nervous system. We'll just call it, this neuron right here. And it's going to leave the central nervous system. Again, it will find another neuron in the peripheral nervous system, and so forth, so on. The other point that I want to make is that the neurotransmitter that is being released from that first neuron in the chain, this is the second neuron in the chain, the neurotransmitter being released in the first neuron in that chain is going to be acetylcholine. And then the neurotransmitter released from the second neuron, if it's parasympathetic, will also tend to be acetylcholine. Now, you have a different situation if we're talking about the sympathetics. So go up here. So if I have a sympathetic nervous system, again, I'm going to have a neuron, and it is going to be in the central nervous system. It will then send its axon out, leaving the central nervous system, and then it's going to synapse onto another neuron, which again is going to be whatever the target is there. It's going to be releasing its neurotransmitters there. And just like the parasympathetic, that is going to be acetylcholine. And then when you get to the end organ, most of the time it's norepinephrine, but it could also be acetylcholine. Sometimes it may even be dopamine. So you have some variation there in terms of the sympathetic system, but dominantly it's going to be, and typically it's going to be norepinephrine. But the point being is that regardless of whether you're talking about the sympathetics or the parasympathetics, acetylcholine is going to be the neurotransmitter that is released between those two neurons. In addition to acetylcholine playing a major role in the autonomic nervous system and then also in the motor end plate or the communication between the nervous system and skeletal muscles, you'll find acetylcholine throughout the central nervous system and other systems. Then the neocortex of the brain, cerebral cortex, is thought to play a role in memory function. One of the pathologies of Alzheimer's disease is a loss of cholinergic neurons. So cholinergic simply means releasing acetylcholine. And I don't want to imply here that a problem with cholinergic neurons or a problem with acetylcholine is the only reason or the only pathological substrate for Alzheimer's. Alzheimer's disease has many, many, many pathologies, and so the loss of cholinergic neurons is just one of many factors that contribute to Alzheimer's. So the cause of Alzheimer's is not simply just losing cholinergic neurons. The cause of Alzheimer's is complex. It is not very well characterized, but what scientists do know that one of the many things that happens in Alzheimer's is that you start losing cholinergic neurons, and many think that that loss of cholinergic neurons plays a key role in the loss of memory function in Alzheimer's patients. Acetylcholine is synthesized in the presynaptic terminal. So again, if you have a neuron and you got your presynaptic terminal there, and then you got some other postsynaptic membrane there, the acetylcholine is actually assembled in that presynaptic terminal, obviously before it is released. And it is synthesized by combining acetyl coenzyme A and choline. And there is an enzyme in the presynaptic terminal, choline acetyltransferase, and that enzyme is a very important enzyme in putting together these two molecules to make acetylcholine. And of course, once the acetylcholine is synthesized, it is stored in vesicles. Then the vesicles will fuse with the membrane and then ultimately be released here. Once you have acetylcholine being released in the synaptic cleft, in other words, that space between the presynaptic membrane and the postsynaptic membrane, you have to have a way of clearing it out. If you can't control the amount of neurotransmitter in the synaptic cleft, then you lose control of the system. So once that presynaptic membrane releases the neurotransmitter, in this case acetylcholine, and then the acetylcholine then will bind to whatever receptor it's going to bind to in the postsynaptic membrane, you have to have a way for that acetylcholine to go away. If you need more acetylcholine, then the presynaptic neuron will release more acetylcholine, but you have to have a way of clearing it out. And there are basically two ways you can control neurotransmitter content in a synaptic cleft. One is that you can reuptake it. In other words, you can have receptors on membranes in the area that can grab that neurotransmitter and put it back into the cell. Another way is that you have some enzymes in that synaptic space, that synaptic cleft, that can rapidly degrade the neurotransmitter. And that's what happens with acetylcholine. So you have some enzymes, acetylcholine esterases. Ases means it's an enzyme, and its job is to rapidly break down acetylcholine. It does it very rapidly. It breaks down acetylcholine into its constituent molecules, choline and acetylcoenzyme A. The acetylcoenzyme A then is just basically used for further metabolism. The choline is actually grabbed and transported back into the presynaptic terminal for use. So we can just kind of clean this up here a little bit. So imagine that I have a choline there, okay, it's sitting right there. There'll be actually a receptor that will grab that choline and put that choline back into the presynaptic terminal, and the choline is reused for another acetylcholine neurotransmitter. You have two general types of receptors for acetylcholine. You have what is called a nicotinic acetylcholine receptor right there, and then you have a metabotropic, a muscarinic acetylcholine receptor. These are two very different types of receptors in terms of function. The nicotinic acetylcholine receptor is a inotropic receptor, which means that once the acetylcholine or once the neurotransmitter binds to it, it functions as a channel. So if you can cartoon it here, and if we let that be our nicotinic acetylcholine receptor, and then if you have acetylcholine binds to the receptor, it actually will then open up, and then it's going to be allowing electrolytes to flow through. In this case, mostly sodium will flow into the cell when the acetylcholine actually binds to it. Actually, it takes two acetylcholine to bind to this receptor for it to open up. Then it becomes basically an ion channel, allowing for depolarization of the postsynaptic membrane. And then you have a metabotropic receptor, okay? And the metabotropic receptor, okay, acetylcholine is going to bind to it. It is not a ion channel itself, so the actual binding of an acetylcholine onto this receptor here will cause second messenger systems to activate, and so what we're talking about here is IP3, DAG, calcium, G proteins, and such. So when the acetylcholine here binds, then there's going to be secondary effects within the cell causing a change in cell biology. It could be involving upregulating, downregulating genes. It could be that it's going to initiate a phosphorylation or dephosphorylation sequence. It could be that the acetylcholine can bind to a metabotropic acetylcholine receptor, and it ends up opening up other channels in the cell membrane, or it may end up closing other channels in the cell membrane. So the effect of acetylcholine on a metabotropic receptor is extremely varied, and it depends upon the cell type on which it is binding. Whether neurons have a nicotinic type of acetylcholine receptor or the muscarinic acetylcholine receptor really depends upon the cell type and what organ system are we talking about. If we're talking about the autonomic system, then the dominant neurotransmitter receptor is going to be nicotinic. And again, when acetylcholine binds to a nicotinic receptor, it's going to be excitatory. It's going to allow sodium to flow in because it's functioning as a channel, and will then tend to want to bring the downstream neuron or downstream organ into an action potential. Interestingly enough, though, while the dominant receptor for the secondary neuron in an autonomic system, whether it's parasympathetic or sympathetic, is nicotinic acetylcholine receptors, you do have some muscarinics there as well. Okay, so muscarinic acetylcholine, let me correct that, muscarinic acetylcholine receptor there. So you do have some muscarinics there, and when acetylcholine binds to those, it can function to actually modulate the activity of the muscarinic acetylcholine receptors. So dominantly nicotinic, but you can have some muscarinic on those neurons as well. And as you recall, when we're talking about the motor neuron innervating skeletal muscle, that's going to be all about nicotinic. So nicotinic, we're talking about skeletal muscle. Okay, that's going to be the big one there. You'll recall in the parasympathetic system where we're talking about the vagus nerve or some of these other nerves that are parasympathetic in the body, and they release the secondary neuron will release its organ here. That is going to be dominantly muscarinic acetylcholine receptor there. Okay, so if we're talking about the autonomics, the end organ, if it is going to be parasympathetic, releasing acetylcholine, it's going to be dominantly muscarinic receptor. If we're talking about a motor neuron that is innervating skeletal muscle, it's going to be nicotinic. And then you have some organs that can have a mixture of both, not necessarily in equal form, but again, this synapse right here, dominantly nicotinic, but you can have some muscarinic receptors on there as well. Also, in many systems, the muscarinic receptor will actually function as an inhibitory neurotransmitter. It will tap down certain biological processes at the end. You have many types of muscarinic receptors, and we'll talk about that a bit later. So before I leave this point, I just want to make sure I'm clear. You have different types of or subtypes of muscarinic acetylcholine receptors, and you also have different types of nicotinic acetylcholine receptors. So again, the type of nicotinic receptor that you would find in a skeletal muscle is going to be different than the type of nicotinic receptor you're going to find perhaps in the autonomics, and could be different than the type of nicotinic receptors you find in the cortex itself. So again, it's not just that you have two kinds of acetylcholine receptors, muscarinic and nicotinic. You do, but within that, you're going to have subtypes of these subtypes. So let's take a look at the term amines. Amines is just a class of neurotransmitters. So amines are going to include norepinephrine, epinephrine, dopamine, serotonin, and histamine. Amines are synthesized in the presynaptic terminal. So just like what we saw with the acetylcholine up here, there are enzymes in the presynaptic terminal that are going to allow that neuron to synthesize whatever neurotransmitter is being used for a particular neuron. And just like we saw in acetylcholine, you have many, many types of receptors for these various types of neurotransmitters. Some of those receptors are going to be inotropic. Some of those receptors are going to be metabotropic. The metabotropic receptors and some subtypes of the metabotropic receptors, some of them will be inhibitory, some of them will be excitatory. And as we saw in acetylcholine, you have different subtypes of these receptors as well. So you can have many subtypes of inotropic receptors and many subtypes of metabotropic receptors. A subclass of the amines, so now we're talking about catecholamine. So the catecholamines are, again, a subset of the amines. And so let's just kind of make this yellow here. So of the amines, the catecholamines are going to be norepinephrine, epinephrine, and dopamine. So dopamine is an amine, but it's also a catecholamine. Serotonin, on the other hand, is an amine, but it's not a catecholamine. So the catecholamines, again, these guys right here, and they're going to be related in terms of the way they are synthesized in the presynaptic terminal. So your beginning molecule, if you're going to be synthesizing a catecholamine, you're going to start off with the amino acid tyrosine, and in the presence of tyrosine hydroxylase, it is going to synthesize L-DOPA. L-DOPA, levodopa is another name for that, L-DOPA. So once you have the molecule L-DOPA, then in the presence of a decarboxylase, it's going to convert it to dopamine. And then dopamine, in the presence of beta hydroxylase, is going to be then converted to norepinephrine. So that's the sequence of event in terms of the synthesis here. And at the end of norepinephrine, actually in the presence of another enzyme, I'm going to add this in here, the norepinephrine can be converted to epinephrine. And the difference between norepinephrine and epinephrine is that a methyl group is added to it. And so you take a norepinephrine, tack on a methyl group to it, and then you have epinephrine. Now the enzyme for that, you'll see it in short as PMNT. And PMNT, and this is a long word here, but I'll go ahead and write it out. It's going to be the phenylethylamine. In methyltransferase. Okay, so PMNT, that is the enzyme that's responsible for converting norepinephrine to epinephrine, and all it's going to do is just tack a methyl group on there. So those are going to be your catecholamines. So what's interesting about this sequence of enzymes and the conversion from one molecule to another molecule is that a neuron, whether it's going to release dopamine as its neurotransmitter or norepinephrine as its neurotransmitter or epinephrine as its neurotransmitter, is going to be dependent upon the presence or absence of these intermediate or these enzymes that we're talking about here. In other words, if you want a neuron to have dopamine as its neurotransmitter, then you're certainly going to be having lots and lots of decarboxylases. So as we said earlier, decarboxylases in the presence of levodopa is going to be converting it to dopamine. If you want dopamine to be the end product, then you don't want these other enzymes present. So if these other enzymes are not present, then the end product is going to be dopamine, and that will be put in the synaptic vesicles. If you're wanting the dominant neurotransmitter to be norepinephrine, then what you're going to need to do is you're going to, of course, have the presence of the decarboxylase to make dopamine, but then you're going to want copious amounts of the beta hydroxylase to take that dopamine and convert it to norepinephrine. And then, of course, if the end product is epinephrine, then you're going to want to have plenty of PMNT. You're going to want to have that N-methyltransferase. Again, methyl means transferase, putting a methyl onto the norepinephrine to convert it to epinephrine, and then that would then in turn be released. Now, what's really interesting about this, it's not binary. In other words, you have a situation where we're going to be violating Dale's principle, where you can have plenty of decarboxylases so that you can have dopamine present, but what if you just have some beta hydroxylase? And therefore you're taking some of the dopamine and you're converting it to norepinephrine, but you're not converting it at all. And then that's a situation where a neuron then could be releasing dopamine and norepinephrine. Maybe you want it to be mostly norepinephrine and just a little bit of dopamine. So again, it's just a matter of regulating the level of that enzyme to convert that molecule to the downstream version. So again, you can see how complex this system can be, and of course you can have cell biology processes that can modulate, either upregulating or downregulating these enzymes, which in turn can regulate the degree in which a neuron can modulate the quantity of the neurotransmitters it could be releasing. Now, another interesting thing here is that when you talk about epinephrine, epinephrine, that's adrenaline, and mostly you associate epinephrine with the adrenal medulla. Okay, that's going to be the inward part of your adrenal glands. And so let's just go ahead and say central nervous system here. Okay, so we'll keep a consistent color. So we have a central nervous system here. And so you have a neuron, a sympathetic neuron. It's going to come out, and it's going to be releasing its neurotransmitters. It's going to be releasing your acetylcholine onto a cell. Now, in the case up here, the release of acetylcholine onto the cell was a ganglia. Okay, ganglia is just a group of neurons outside the central nervous system. Well, when it comes to the adrenal medulla, what we're basically we are releasing acetylcholine on these cells in the inward part of the adrenal gland, known as the adrenal medulla. So the acetylcholine is going to be released there. The dominant neurotransmitter receptor there is actually going to be nicotinic acetylcholine receptors. Okay, so you're going to have nicotinic acetylcholine receptors. It's going to depolarize. And then what's going to happen within these cells there, they have the enzymes to make lots and lots and lots of epinephrine. So then they're going to be releasing epinephrine into your bloodstream, and then it's going to be carried out through the rest of your body. Another general point about neurotransmitter receptors, and I'll just kind of draw a receptor there, is that you have a neurotransmitter, okay, and it binds to the receptor. These proteins can have other binding sites for other things as well. So many of these receptors can be sensitive to hormones. So the binding of hormones to these receptors can alter the function of these receptors. These receptors can have binding sites for drugs. Again, different binding sites that can then influence the behavior of these receptors. Many of these receptors have binding sites that toxins can bind to, and again, affecting the function of the receptor. So the receptor is pretty complex in the sense that it can not only necessarily bind to neurotransmitters, but it can bind to other things at other binding sites. I want to say a few more things about the catecholamine dopamine, and I want to take a look at dopamine in the context of a well-known pathology, as you know, Parkinson's disease. Parkinson's disease is defined as having a loss of certain types of neurons, and these neurons make dopamine, and when these neurons die, that's when you have Parkinson's disease. So let's just sketch this out a little bit. So you have in your brainstem, you remember your brainstem is divided up into three areas. You have a midbrain. Then below that you have a pons. And then below that you have the medulla, or the medulla oblongata. And then after that you have your spinal cord. So there is an area in the midbrain called the substantia nigra. And the substantia nigra, as the name implies, literally means dark substance. When you slice through the midbrain and you look at a cross-section on a slide, there's going to be a very dark region. That's your substantia nigra. A part of that substantia nigra is loaded with dopaminergic neurons. And these neurons are going to project to other areas of the brain, and they're going to deliver dopamine to those areas of the brain. And when somebody has Parkinson's disease, those neurons, those dopaminergic neurons that reside in the substantia nigra of the midbrain, die. No one knows why they die. No one knows what the trigger is. Could it be genetic? Could it be environmental? No one knows. Now we know it's not purely genetic, and we know it's not purely environmental, but yet the causal chain that leads to the particular death of these neurons is still, by and large, unknown. But what I want to do for you to help you understand Parkinson's, I just want to talk a little bit about how the substantia nigra, when it's working normally, how it influences motor activity, because we know one of the major hallmarks of Parkinson's is abnormal motor activity. So I'm just going to kind of scheme it out for you. And so I'm just going to say, we'll just go a different color here, say we have an area in the brain, okay, and that area in the brain is involved in motor function. So I'm going to go motor area. You got lots and lots of motor areas, but and I'm not going to go too much into detail with this, but you have some areas deep in your brain that is a type of motor area, and the job of that motor area is to coordinate movement. It's to coordinate the flexing, the contraction and the relaxation of muscles. So imagine the following. When you are moving your forearm, you can either flex your forearm, which is bringing it closer to your body, or you can extend your forearm, which would mean making your upper extremity straight. Well, when you flex your forearm, then that means one of the muscles you're going to be contracting is going to be your biceps. But during that flexing of your forearm and the contraction of the biceps, at the same time, you're going to be relaxing the antagonistic muscle group, which in this case would be your triceps. So you can have two general classes of muscles that are moving your joints. You have your flexors, and you have your extensors. And so your biceps would be an example of a flexor, your tricep would be an example of an extensor group. And they're antagonistic to each other. So if when one is contracting, you want the other to relax. Well, for that coordination to happen, you have neurons sitting up here in this deep motor area, and they are going to, through a system of other neurons, they're going to coordinate the contraction of the extensors relative to the flexors. So if you want to move your forearm or flex your forearm, then this motor area that's deep inside your brain is going to coordinate all of that movement, and that's going to then ensure that you have a successful coordinated movement of flexing of an arm or extensing of an arm. But it's going to involve the stimulation of one of these groups and the inhibition of these other groups. So what happens is that you have, I'm just going to say right there, that's going to be your substantia nigra. It's going to be in your midbrain over here, okay? So the neurons in your substantia nigra, the ones that make dopamine, and I'll just go a different color for kicks, these guys are going to heavily influence that deep motor area that's responsible for coordinating your movements of flexors and extensors. And so they're going to be delivering lots and lots of dopamine onto this system here. And as long as it has the appropriate amount of dopamine, then this deep motor area of the brain can do its job in terms of having a smooth execution of a movement. So what happens in Parkinson's disease is that these neurons that have the dopamine, they're going to start degenerating. They're going to be reduced in number. Therefore, that means there's going to have a reduction in the dopamine delivered to that deep area of the brain responsible for coordinating all these movements. And so when these neurons start to die, then you have your Parkinson's types of movement disorders or pathology. Now, most of the time, the movement disorder that we associate with Parkinson's is going to be resting tremors. Your hands are shaking or other parts of your body are shaking when you're at rest. The fact of the matter is not all Parkinson's patients have resting tremors. Most of them do, but some of them don't. But one of the things that all Parkinson's patients are going to have is going to be freezing. In other words, they're going to be executing a movement or trying to make a movement, and then all of a sudden they can't move. And part of what's going on with the freezing is that when you have simultaneous contraction of the flexors and at the extensors at the same time. If your biceps are contracting and your triceps are contracting at the same time, you literally lock that joint in. In other words, it becomes frozen. You can't move. And so, again, the mechanism is poorly understood, but you'll have a moment or a period where the Parkinson's patient, they'll have the joints that will freeze, and then they'll unfreeze. Now, the movement after the unfreezing is still abnormal because of what's going on up here, but you do have that freezing. So that's very common across all Parkinson's patients. It's very painful and very difficult to manage. There are other systems in the brain that are affected by Parkinson's in addition to these motor areas, and so the symptoms of Parkinson's involves more than just movement disorder, but that tends to be the main effect that gets all the attention. So that's kind of the setup. So if someone has Parkinson's and their substantia nigra dopaminergic neurons are degenerating, then what can one do? Well, one of the pharmacological strategies is to give the patient L-DOPA. Now, we saw L-DOPA up here, that's levodopa there. That's a precursor to dopamine. So a question would be, if they are low in dopamine, just give the patient dopamine. Give it to them in IV or give it to them orally. The problem is dopamine cannot cross a blood-brain barrier. So in the literature, you'll see a blood-brain barrier is B, blood-brain barrier. Now, I think the better term for this is going to be the central nervous system barrier, or the central nervous system blood barrier, because the blood-brain barrier also includes the spinal cord as well. So you have capillaries going into the central nervous system, spinal cord and brain. And the issue is that there are a lot of molecules in plasma that if they were to be exposed, but if the brain or central nervous system were exposed to those molecules, then you would have a toxic effect. So you have a lot of neurotoxins that are normally in your plasma. Again, your body needs these molecules for other things, but they don't do well when they're in the central nervous system. So as you may know, your spinal cord, your capillaries are very leaky throughout your body from varying degrees, but when it gets to the blood flow to the spinal cord and the brain, you have a barrier formed. The barrier is formed by the endothelial cells that make up the capillary, and the quality or the nature of the endothelial cells that make up the capillary in the central nervous system are such that they're tightly locked in. In other words, they're sealed off. So the blood-brain barrier or the central nervous system barrier is very, very selective in terms of what it's going to allow from the plasma into the central nervous system, because it's trying to keep those bad things out of the central nervous system. Well, for better or for worse, the dopamine cannot go across the blood-brain barrier or the blood central nervous system barrier. So giving the patient dopamine, trying to replace a dopamine that's lost in this deeper motor area, doesn't do much good. So why give L-DOPA? Well, the cool thing about L-DOPA is that L-DOPA, in fact, can cross the blood-brain barrier or the central nervous system barrier. Blood barrier. So you can give L-DOPA. The L-DOPA gets into the brain, and then the enzymes that are there to convert levodopa or L-DOPA into dopamine are present, so they can take that L-DOPA and they can convert it to dopamine, and this actually will help a Parkinson's patient. It won't completely solve the motor movement disorders, but it will tap them down in a significant way. So this can be a very effective drug to give a Parkinson's patient. Now, sadly, given the Parkinson's patient, L-DOPA only works on the front end of the disease. So after a year or two, eventually the L-DOPA is not going to work. It's going to become ineffective, And the thinking on that is because you've just had so many other neurons that have died in the substantia nigra that not even L-DOPA can help with that. But here's an interesting thing about this, and that is if you just give the patient L-DOPA, that's not going to work very well. Because the problem and the challenge is that L-DOPA is converted to dopamine in the brain, but also L-DOPA is converted to dopamine in the non-central nervous system area as well. And dopamine has an effect on the non-central nervous system part of the body. Dopamine in the regular body has a huge influence on your cardiovascular system. So it's dose dependent, but low levels of dopamine will actually cause hypotension, low blood pressure. High levels of dopamine will actually cause hypertension, high blood pressure. So if you load the patient up with L-DOPA, a portion of that L-DOPA is going to be converted to dopamine in the non-central nervous system part of the body, and you're going to have all kind of cardiovascular challenges with that. Also, you're wasting a lot of that L-DOPA. That L-DOPA is meant to go to the brain so it can do its job, but you're spending a portion of that L-DOPA in the non-central nervous system part of the body, which is not particularly a good way to go. So the solution to this is to pair L-DOPA with another drug called carbidopa. And carbidopa is actually going to inhibit the decarboxylase. So carbidopa is going to stop or inhibit the conversion of L-DOPA to dopamine. But you say, wait a minute, then won't it do the same thing when the L-DOPA is going into the central nervous system, so you kind of defeated the purpose? That would be true except one thing. The carbidopa also cannot cross the blood-brain barrier or across the blood-central nervous system barrier. So you're keeping the carbidopa in the peripheral part of the body. You're keeping it out of the central nervous system. So it keeps the L-DOPA in the non-central nervous system part of the body from becoming dopamine, which addresses your cardiovascular challenges, and it also preserves that L-DOPA so that more L-DOPA then can get to your brain and be converted to dopamine, therefore addressing the challenges you have in terms of the movement disorder for your Parkinson's patient. So L-DOPA and carbidopa are given at the same time. In fact, many of the pills you have out there, the L-DOPA and the carbidopa is in the same pill as you give it to or as you administer it to the Parkinson's patient. So I just wanted to introduce you to, again, the concept of how Parkinson's disease and dopamine are related to each other. In addition to its role in Parkinson's disease, I want to explore a little bit more about dopamine. Dopamine is found throughout the brain, and it's involved in many, many functions. And one of the things it does is it plays a critical role in personality. So it plays a heavy role in personality issues or personality function in the frontal lobes of the brain itself. It is thought that hyperactive dopaminergic neurons in some parts of the brain could be very much involved in some forms, maybe many forms, of psychosis. So that's kind of the dopamine hypothesis theory, that there's association of abnormally high dopamine different areas of the brain. It is also thought that this could be involved in some forms of schizophrenia. It is thought that dopamine could be also involved in bipolar disorders as well. So dysregulation or loss of appropriate regulation of dopamine in many areas of the brain can lead to a lot of behavioral problems. When it comes to psychosis, there's a drug, chlorpromazine. That is a common drug that is used with many psychotic patients, and its mechanism is to inhibit the dopaminergic neurons. In other words, to tap them down so that you have a more normal level of dopamine, and that then in turn brings the patient back to a little better state. It's not a cure-all, it's not a magic bullet, but it seems to help in managing psychotic episodes. Chlorpromazine is not the only drug. There are other drugs that have similar mechanisms. This one that's fairly common. Dopamine is very, very important also with our sense of pleasure. So I want to do a little bit of anatomy here for you. So you'll recall that we had midbrain, pons, medulla. There is another area of the midbrain. I'm just going to go a circle there, and that is going to be called the ventral tegmentum area. And you'll see this in literature as the VTA. It's near the substantia nigra. It is also loaded with dopaminergic neurons. And the VTA in the midbrain projects widely to many, many very important areas of the brain, particularly the frontal part of the brain that drives behavior and personality. So this is part, or a vital part. The VTA is a vital part of what is called the pleasure center. So the pleasure center is actually an area in your frontal area of your brain, but the VTA is a component of that because it projects strongly, the VTA from the midbrain projects strongly to the pleasure centers in the frontal part of your brain, releasing lots of dopamine. And so when you have a sense of euphoria, when you have a sense of well-being, of pleasure, then the VTA is upregulating the amount of dopamine that is being released onto the official pleasure centers in the front part of the brain, and then you have this subjective experience of feeling really, really good. And whether it is a type of pleasure you would get sitting in a chair watching a beautiful sunset, or the type of pleasure of intense euphoria associated with an orgasm, sexual pleasure, or everything in between, all of it revolves around dopamine, revolves around the VTA, and revolves around the pleasure centers in the frontal area of your brain. I am not suggesting that dopamine is the only neurotransmitter involved in pleasure. It is not. But what I am saying is that it is a key component, and that when you elevate the dopamine levels in those areas, you're going to have a subjective sense of pleasure. Now, speaking of pleasure, let's take a look at some drugs here. Cocaine is the first one I want to take a look at, and I'll just say some brief things about that. Well, I think we all know what cocaine does. So when you do a line of coke, you're going through your nasal cavity and you're inhaling it. Cocaine actually was first developed as a numbing agent, so like Novocaine, cocaine. So it will actually shut down voltage-sensitive sodium channels and will have a pretty effective numbing effect. But it also affects other areas of the brain. In particular, what cocaine will do is that it will inhibit the reuptake of dopamine. So you'll recall in an earlier lecture, we spoke of how levels of neurotransmitters are being regulated in the synaptic cleft, and we talked about acetylcholine being broken down by an enzyme, but then other neurotransmitters, they have to be reuptaked. In other words, if you have a, releasing here, okay, and then we have another neuron, say here, all right, and then you have these neurotransmitters, in this case dopamine, being released. Well, I have other little proteins sitting up there, and their job is to grab the dopamine and return it back to the presynaptic terminal. And so what happens is that the cocaine will go in and it will inhibit those proteins, those reuptake proteins, keeping them from being as effective in reuptaking dopamine. Therefore, the level of dopamine in the synaptic cleft goes up, therefore having an effect on the downstream neuron. So that's basically how cocaine works, at least in terms of the dopamine story, is that it's going to inhibit the reuptake of dopamine. End result is it's going to be increasing the level of dopamine, therefore increasing the level of pleasure when we're talking about the dopaminergic neurons that are in your pleasure center in your frontal lobes of your brain. Now, the difficult thing about cocaine, I mean, it does other things as well, okay? It's going to affect other systems. But when you are chronically taking dopamine, it has other effects that are not particularly desirable. And so, for instance, you have your dopaminergic neurons that are sitting over here, dopaminergic receptors, that are sitting here on this neuron. So when the dopamine binds to it, of course, it has the effect that it has. But when you have use of dopamine over time, you can actually develop a tolerance for dopamine, and it's the same mechanism as you would have a tolerance for many drugs, in the sense that, and again, the mechanism is understood, but somehow this system senses that there's too much dopamine in the synaptic cleft, and what will happen is that these receptors will downregulate and they will become non-functional. They may be taken out of the membrane itself, or they may be something happens to the receptors so they just simply don't function. But the bottom line is you're reducing the number of functional receptors for the dopamine with long-term use of dopamine. So you quickly develop a tolerance. So the level of euphoria, the level of buzz that you get the first few times you do a line of coke, after you do it for a week or so, all of a sudden you don't get that euphoria again. So what do? You start, using more and more and more cocaine to try, chasing that initial effect. Another difficult aspect of cocaine use in pleasure center is that you have also what is called reward centers in your brain. And again, it's a collection of a series of nuclei in your brain. Some people would call this an addiction center. But basically what it's telling you is you're involved in an activity. Ooh, this feels good. I want to do it again, and I want to do it again, and I want to do it again. And so that alters the circuit, which in turn then alters behavior, alters judgment, and then you start engaging in that same behavior pattern over and over and over again to the point to where now you become, quote, addicted to a particular activity. And so you can become addicted to cocaine. As somebody said one time in an interview, they were asked, what does cocaine make them feel like? And the answer was, cocaine makes me feel like taking more of cocaine. So it's just an endless loop, and then the more you take it, the more downregulation you have, which makes you want to take it ever more, etc. And so it's just basically an endless cycle, and that takes you to a very bad place. A couple other items about cocaine, just for your information. There are different kinds of cocaine. So you have your regular powder cocaine. That's the one you're always, you see on TV or whatever, you put it up your nose. Other forms of cocaine is you have free base cocaine. And free base cocaine is the purest form of cocaine. In a sense, you've liberated it from its salt base. And so to get free base cocaine, which is much more potent than regular powdered cocaine, the process you have to get there, though, is you have to use some volatile chemicals that are extremely inflammatory. And so it's a pretty dangerous process to try to convert regular powder cocaine to free base cocaine. But some people try it, and then when they take free base cocaine, it's a more potent type of experience for them. The other is crack cocaine, and crack cocaine actually is such that you take powdered cocaine, you mix it with baking soda, you heat it up, and the baking soda, cocaine interact, and it comes out as crack. And the reason crack cocaine is so popular, or can be so popular, is that you can smoke crack cocaine. If you had the regular powder cocaine, You can't smoke it. The melting temperature is way too high. But crack cocaine, as well as freebase cocaine, actually you can smoke either one. You can heat it up, and then you can inhale the gas form of it. And the reason that this is so appealing to users is that if you're taking cocaine in an inhaled form, it gets to your brain much more quickly, and you have a more intense high because of just the speed with which it can get to your brain, and it's pretty potent, actually. The other thing, too, is that you can inject crack cocaine into your veins. Again, gets it to your central nervous system very rapidly and more effectively than simply taking powder cocaine and putting it up your nose. Potential side effects of cocaine are actually can be kind of scary. They can cause, significant headaches. It could put you in seizures. It could cause heart problems, because a heart attack. It can cause a sexual dysfunction, could damage your lungs. Again, there's just a whole lot of various things happen, none of which are good regarding long-term use of cocaine. So can't think of one good reason to actually use that. Let's take a look at another drug, nicotine. We all know what nicotine does. Nicotine also can cause the elevation of dopamine in the brain. It does so at a more of an indirect way. Nicotine binds to nicotinic receptors, so nicotinic acetylcholine receptors. We talked about that earlier. So nicotine will bind to these receptors, and then those downstream neurons will talk to other neurons, and then the end result is going to be an increased level of dopamine, particularly in the pleasure centers of the brain. So yes, it is going to involve the ventral tegmentum area as well, but it does so in an indirect way. One side note here is that I just told you that nicotine binds to nicotinic acetylcholine receptors. And I also said earlier that there are different types of nicotinic acetylcholine receptors. And so what I'll tell you is that nicotine actually has a low affinity for the nicotinic acetylcholine receptors associated with a skeletal muscle. So the neuromuscular system that causes skeletal muscle to contract, nicotine can bind to it, but the affinity is pretty low. But the main effect of nicotine is not going to be on those neuromuscular junctions, again, because of low affinity of that type of nicotinic receptor, acetylcholine nicotinic receptor. But you have another type of nicotinic acetylcholine receptor in your brain where nicotine is very, very good at binding to it. So it has a much higher affinity for those nicotinic receptors that are located in the brain compared to what you have in your neuroskeletal junction here. Which again is why the nicotine's most of its main effect is going to be in your brain and not your muscles. So again, it binds to those receptors and ultimately will lead to an increase in dopamine in the brain. So you derive some type of pleasure, obviously, from taking in nicotine. Nicotine, though, is probably the most addictive substance known to humans. So the various mechanisms by which nicotine works, again, not clearly worked out, but it literally can rewire your reward center. It will change the circuits up, and it does so permanently. So when somebody has chosen to take in chronic levels or high levels of nicotine for long periods of time, it literally is going to change the brain such that when you stop the nicotine, the brain never goes back to the way it was before you were exposed long-term to nicotine. So if you have an individual and they smoked 2 packs of cigarettes a day for 20 years, and then they stop smoking and they haven't smoked for 15 years, their brain is still permanently changed. It never goes back to the way it was. And in fact, you'll talk to some people who struggle with nicotine addiction, and they maybe smoked 2 packs for 20 years. They quit. They hadn't had a cigarette in 15 years. But some of them will still tell you, I get up in the morning and I still have a desire to smoke a cigarette. So it's pretty much a one-way street when you're talking about nicotine and how it reworks your brain in an irreversible way. And of course, the reworking or the rewiring of the brain is it's driving that behavior to take in more nicotine. Now, what's really kind of scary about this is that the younger the brain, the more susceptible it is for rewiring. So if you have somebody who's 12 years old and they start smoking and smoking a lot, it's much easier for the nicotine to rework their brain so that there's a better than even chance that they're going to be a smoker for life. So the younger the brain is exposed to nicotine, the more intense the rewiring becomes, and of course it still is quite permanent. But that is why for people who smoke, most people, they started smoking when they were a teenager. Nobody goes through life having never smoked a cigarette. They wake up on their 60th birthday and then start smoking cigarettes. That just doesn't happen. So that's why, again, it is the early habit of smoking that changes the brain, but it's always, begins at a younger age when the brain is a little more plastic and more susceptible to the rewiring. The bad thing about like cigarettes and such is that cigarettes and such are loaded with toxins. So nicotine is not the only bad thing in cigarettes. So there are toxins in there that are going to be affecting brain function other than nicotine. There are toxins in there that are going to have a deleterious effect on your cardiovascular system. They're going to have a deleterious effect on your lungs, of course promotes lung cancer. I mean, the long laundry list of all the bad things that happen when you have chronic smoking habits. And so you got a lot of other toxins in a cigarette. And so if you were some evil entity and you wanted to create the perfect killing machine, what you do is you take the most toxic thing known to humans, you take a whole bunch of toxins, you roll them up into one thing, and we call it a cigarette, and then you sell it. It's the perfect killing machine. Very tough, very sad. But that's kind of what goes on with the cigarettes is not only does it have a long laundry list of health issues, it literally is going to irreversibly rewire your brain, driving you to always wanting to desire a nicotine effect. Cocaine will also rewire the brain, not to the degree that nicotine does, but cocaine can also have that effect. In fact, what you're going to find out is that there are many other types of drugs, the opioids and such, they also rewire the brain, really working on this reward center. But as far as the king of rewiring the brain, I think nicotine is pretty much the one that wins that battle. All right, so we'll see you next time. Let's turn our attention to another neurotransmitter, serotonin. And serotonin is 5-hydroxytryptamine, and you'll see this very often as 5-HT. Serotonin plays a role in temperature regulation in the brain, and that is, of course, going to involve the hypothalamus. Serotonin is involved in sleep onset and also plays a major role in mood. Serotonin also is a major player in pain modulation. So it's a pretty busy molecule. Serotonin is also very active in the peripheral nervous system, particularly the GI system as well. Again, my goal is not to go through all the things that serotonin does, but basically to let you know it's a pretty active neurotransmitter throughout the body. You have many, many types of serotonin receptors, 5-HTRs. The vast majority of them are metabotropic. There's one type that is inotropic. The rest are metabotropic. And again, as I've said, you even have subtypes of subtypes. So the role of serotonin in terms of what it's going to do to the downstream biology of the cell is quite varied. We usually will see serotonin associated with antidepressants. It is thought that one of the possible mechanisms for those that struggle with clinical depression is too low a level of serotonin. The bottom line is no one understands the neurobiology of depression. We think we have a few ideas of what may be going on, but the full story has yet to be told. It is quite possible that some types of depressions involve serotonin issues. There may be other types of depressions that don't. Serotonin is not the only neurotransmitter involved in depression. There are other neurotransmitters, whether it be dopamine, whether it be norepinephrine, that may also be involved, and there may be other neurotransmitters we're not even aware of. So I do not want to oversimplify the neurobiology of depression. Having said that, since some believe that some type of depressions are based in too low levels of serotonin, one of the pharmacological approaches is to give the patients, or to give a patient something that will elevate the level of serotonin. And as we have spoken of before, many of the neurotransmitters, when they're released in the synaptic cleft, the level of those neurotransmitters are controlled by how aggressively they undergo uptake by the presynaptic terminal. So you have these receptors in the membrane of the presynaptic terminal, and their job is to grab that neuroreceptor and grab that neurotransmitter and put it back into the presynaptic terminal. Well, we have serotonin that does the same thing. So one of the strategies is to come up with a drug that will inhibit the reuptake of serotonin, thereby elevating the level of serotonin in the synaptic cleft. And so we call these drugs SSRIs, and that's selective serotonin reuptake inhibitors. And they will actually inhibit the reuptake of serotonin, thereby elevating the level of serotonin in the synaptic cleft. Now, what's complicating about this is that, first of all, it takes multiple weeks to have an effect. So one would think that if the problem is just simply too little serotonin, that once you start inhibiting the serotonin reuptake, that the result would be pretty quick. And that's not the case, which then further suggests that there may be other things that we're not understanding about how even the serotonin reuptake inhibitors work. So typically what you would put the person on an SSRI, and you would give them a regimen in terms of dosing, and you would not expect any type of therapeutic effect until 3-4 weeks downstream. Then you may start having an effect. Now, when they did the trials to see if this actually did anything for people who were depressed, as you would guess, you have to have a placebo group, and then a control group, and then you have the group of people that are, clinically depressed. You have all these metrics in terms of how to measure mood and such, and usually the results are going to be the following, or were historically, is you have the two groups of people. You give them the medication. Again, it's double blind, so neither the practitioner or the scientist knows what the patient is getting, nor does the patient know what they're getting in terms of the placebo or the drug. So hence double blind. And so the results are, as soon as you give both populations some type of drug, whether it be placebo or not, almost everybody feels good the next day. Well, you know that has nothing to do with the medication. It's just the fact that you're taking something that you think may alter your mood, makes you feel better. So the way the data is going to shake out is that initially everybody, or the vast majority of the people, are going to feel better. And then over a period of weeks, the group that got the placebo will return to baseline, and then the group that did not get the placebo, some of them will return to baseline, but some of them won't. But you won't see that effect until multiple weeks out. And so the statistics is fairly clear, in that the SSRIs can be effective up to a statistical significance, makes actually a difference in the patient. Now, what I am not saying is that if you have someone depressed, you put them on an SSRI, they're going to become undepressed. That isn't what happens. There is a significant number of people that struggle with depression, and the SSRIs have no effect on them whatsoever. But some people, it's a godsend. We don't understand why some people respond to this and others don't. We don't understand why it takes 3 or 4 weeks for there to be a therapeutic effect, if it's going to happen at all. Now, these SSRIs are not a happy pill. So a person doesn't get a buzz out of taking an SSRI. So it's not a pill or it's not a medication that actually is abused on the street, because there's no reason to do it, because it doesn't make you feel euphoric or anything like that. It's not a magic pill. What patients will report is that the serotonin it's not a mood elevator in terms of giving you a buzz. It just makes you feel not depressed, and that's usually how it's reported. Now, the SSRIs are not designed, nor should be taken, for someone who is basically just going through, you got the blues, you're bummed out about something, you made a bad grade, or something's upsetting you, so you pop a couple of SSRIs, and all of a sudden everything's going to be well again. This is not that kind of drug. This is for the clinically depressed, chronic, and this is one of the go-to drugs that you would go to for that. Fluoxetine, which is Paxil. Fluoxetine is Prozac, and then paroxetine is Paxil. Escitalopram is going to be Lexapro. And sertraline is going to be your Zoloft. I think probably Prozac or the fluoxetine was actually the first one. Again, these can be effective in some people. Now, one of the common side effects for the SSRIs is that they will cause certain sexual dysfunctions. One of the common complaints of the SSRIs is that it renders the patients what is called anorgasmic. It doesn't cause impotence in males, it just causes anorgasmic in both females and males, which basically it's interfering with your sexual pleasure, and it basically, in some people, takes away their ability to have an orgasm. And that's a real problem for some population, in the sense of they have a depressive situation, clinically depressed, they take a drug, it helps them with their depression, but they can no longer enjoy sex. And, and for some people, they'd rather have the depression and enjoy sex than the other. It does not affect everybody that way in terms of making them anorgasmic, but it does some people. So that is a complaint with a significant population out there, and that would be one of the main reasons why you have non-compliance of someone who is struggling with clinical depression relative to just not wanting to take the drug. For reasons that we do not understand, but these SSRIs can also be very helpful with functioning as an anxiolytic or an anti-anxiety medication as well. Again, the neurobiology is not well understood, but people who are struggling with panic attack disorders or general anxiety disorders, PAD and GAD, for some people, this is one of those things that could be helpful. Again, it doesn't help everybody. Now, when we're talking about people who struggle with debilitating anxiety or debilitating depression, this is very much an organic thing. It is something having to do with the neurobiology, and when you're dealing with somebody that is in that particular mode, many times words coming out of your mouth isn't going to make any difference. So it's not particularly useful to tell somebody if they're depressed to just snap out of it or think happy thoughts or go eat some ice cream or whatever. Those kinds of things don't work, and in fact can be very hurtful, because the person on the other end is feeling absolutely helpless relative to their mental state, and these little quick fixes typically don't work. So these people need some sort of intervention, pharmacologically speaking, that would help them out. I'm not saying that talk therapy is useless in the types of depression and anxiety that's out there, because it can be useful. And for some people receive relief from anxiety and depression through talk therapy, and that's a wonderful thing, and that would be preferable to taking drugs. But there's a significant population out there that struggles with this, where talk therapy in and of itself does not help. And so for some, it's a combination of talk therapy and drugs or pharmacological agents. Other people don't even have to fool with the talk therapy, they'll just take the drug. What I'm saying is heterogeneous, and it's complex, and it is poorly understood. But again, for a lot of people, these SSRIs have been an absolute lifesaver in terms of their quality of life. There's another drug out there, venlafaxine, or Effexor. That is a different class. It is called a serotonin and norepinephrine reuptake inhibitor. So this would be an SNRI type of drug. So not only is it affecting serotonin, it is also affecting norepinephrine as well, elevating the levels of norepinephrine. Because as I said before, depression is it involves multiple neurotransmitter systems. So typically what you would have as well when you're dealing with somebody with depression is if one drug doesn't work, you put them on another drug. And so typically what will happen is you have somebody, clinically depressed, long-term, chronic. You just kind of go through the various antidepressants that are out there, trying to find one that works. And there have been plenty of people out there that the SSRIs did not work, but the SNRIs did work, and vice versa. And there's some other antidepressants that we'll talk about in a moment. But again, the SNRIs is another class, and it's working on both serotonin and norepinephrine in terms of elevating the levels of those neurotransmitters. You have atypical antidepressants. An atypical antidepressant works by changing the levels of one or more neurotransmitters, such as dopamine or serotonin or norepinephrine. Each one of them works a different way. Again, just trying to come up with a combination of neurotransmitter tweaks that will help the patient dealing with their clinical depression. Bupropion is one of those that falls in this category, as well Wellbutrin in terms of the trade name. These tend not to have as much sexual side effects as, say, the SSRIs do. And so for people that are complaining about the sexual side effects, you may end up just trying to put them on the bupropion or the Wellbutrin, or bupropion, sorry. Anyway, so again, one more tool in the toolbox. You have some older class neurotransmitters called MAIOs, and these are monoamine oxidase inhibitors. That doesn't make sense unless you know what monoamine oxidases do. Monoamine oxidases are found in the presynaptic terminal. They're associated with the mitochondria that live in the presynaptic terminal. And their job is to break down monoamines, such as serotonin, norepinephrine, dopamine, and such. So if you have an amount of neurotransmitters, in this case, maybe serotonin, in the presynaptic terminal, well, not all that serotonin is recycled and used again. So you have this kind of push-pull in the sense of some of it is recycled, but others of it is simply broken down by the enzyme in the presynaptic terminal. And that's the role of your MAOs, is to break down these neurotransmitters in the presynaptic terminal, because you don't want to have too much of a buildup. And so it's part of the regulation in terms of how much is there in the presynaptic terminal to begin with. So one of the approaches would be, if you wanted to elevate these neurotransmitters, simply start inhibiting their breakdown in the presynaptic terminal, which would then raise the level in the presynaptic terminal, which would then in turn have a higher probability of them being grabbed by the transporter that's going to grab them from the presynaptic terminal, put them into the presynaptic vesicle, such that in the end, more neurotransmitter gets released because you have more neurotransmitter in the presynaptic terminal to begin with. And so that is an approach. This is an older drug, and there are problems with it in the sense that with the MAOI receptors, drugs, is that there are certain dietary restrictions that you have to have. There are certain foods that you can't eat because the breakdown of the food is driven by monoamine oxidases. I'm not going to get into the details on that. If you're really interested, you can look it up on Google. So that's one of the limitations for the MAOIs. You have different types of MAOIs. You have MAOs. You have an MAO type A, MAO type B, and they're specific to various amines in terms of breakdowns. But the strategy is, if you can inhibit these guys, you'll raise the level of neurotransmitters. And then the last one, and this is also an older drug, and it's called a tricyclic antidepressant. And through other types of mechanisms that don't necessarily involve an SSRI type, they're going to be elevating the level of serotonin and norepinephrine. The mechanism is different than your SNRIs, but they get to the same point. So you have all of these drugs that are potentials for helping someone that is struggling with clinical depression or even perhaps anxiety. Okay, so again, just kind of a bird's eye view of what goes on with serotonin and the drugs that would actually alter the serotonin system in the central nervous system. Okay, so we'll leave this here. We'll pick up next time. Treatment of neurotransmitters. Histamine is a neurotransmitter. We normally talk about histamine as being part of your, an allergic reaction. You get a bee sting or mosquito bite, you'll have histamines are going to be released from the mast cells and so forth, so on happens. Well, true, but histamine is also functioning as a neurotransmitter. You'll find it commonly in the hypothalamus, part of the central nervous system. It may be involved in sleep-wake cycle. It may be involved in terms of your conscious awareness. Again, the effect that histamine has in the central nervous system is still being worked out, but it seems to be involving those sorts of things. We have neurotransmitters that are just straight up amino acids. Glycine is one of these neurotransmitters. Glycine typically is an inhibitory neurotransmitter, and it is found on neurons associated with the spinal cord. So you have these little itty-bitty neurons called interneurons. And interneurons are just simply small neurons that just affect local circuits. And so you have interneurons in the spinal cord and also in the brainstem. And their job is, in a sense, to kind of put the brake pedal on excitation. So I'm just going to oversimplify this, but just to kind of draw it out for you. You have a neuron coming from the brain. I'm going to go brain up here. And it's going to come down to the spinal cord, and we'll talk to another neuron in spinal cord. I mean, this could be the brainstem as well. And then that neuron is going to leave the spinal cord, and then it will make a connection with a muscle fiber. And of course, it will release its acetylcholine binding to nicotinic receptors, and you have a muscle twitch. So if you're wanting to move a particular part of your body, the signal will come from the brain, and it will release its neurotransmitters, which will cause action potentials down this motor neuron, and then that will then release acetylcholine, and you get your muscle movement. So that's a simplified version of what's going on. Well, also what happens in the system, and we'll just go green here, is that I'm also going to have little neurons in the in the brainstem or the spinal cord, and they're going to come on, and they are going to be releasing glycine And they could also release some GABA too, so I'll talk about GABA in a second. But the bottom line is that they are inhibitory. So they are tapping down the action potential frequencies of this motor neuron going to the muscle. And you say, well, what's controlling the glycine neuron? Well, you got several things. I'm just going to oversimplify and say that you have other regions in the brain that are coming down talking to it and maybe stimulating the inhibition. So what you have when we're talking about a movement of a muscle in terms of excitation and inhibition, it's just easy to think in terms of an accelerator and a brake pedal. So I'm having both going on at the same time, and this is true throughout your central nervous system, where I'm pressing the brake and I'm expressing the accelerator, the brake being inhibitory, the accelerator being the excitatory. So any movement you have, anything's going on, you have the brake and the accelerator both being pushed on. So it's just a matter of relative how much you push on one versus the other. So this is all the time going on. You're always having signals coming from the brain to create a certain tension on the muscle. You're always having signals coming down from the brain, stimulating the glycine to inhibit the signals going to the muscles. So that's just kind of the state of affairs. Anything that is going to interfere with that glycine function could have a problem. And so just for example, you have a certain poison called strychnine. You may have heard of it. And strychnine is an antagonist for the glycine receptor. So if I'm in the glycine receptor is going to be sitting on that motor neuron there. So if it is going to be interfering with that, so now what you have is you have a releasing of the brake, which then causes uncontrollable transmission of signals to the muscle fiber, thereby causing a problem in movement. Now, this is maybe an inconvenience, except if you're talking about the skeletal muscle called the diaphragm. And then if you're basically rendering the diaphragm non-functional, then that would be a way that it could kill you. So again, that's just an example of how you could interfere with the glycine system, which would then cause all kinds of motor problems because you're messing with that delicate brake pedal accelerator dynamic. Another interaction of the glycine system would be tetanus. Again, tetanus, you got a bacterium in the soil, anaerobic. It is picked up, it is transported from the neurons in tissue, transported back to the spinal cord or the brainstem, and the tetanus toxin can interfere with glycine function, again, leading to uncontrollable contraction of muscles. So again, another way that glycine is involved with this. Another neurotransmitter that's inhibitory is going to be gamma-aminobutyric acid, or GABA. We've talked a lot about that. It is the most common inhibitory neurotransmitter in the central nervous system. Estimated about a third of all the synapses in the central nervous system are GABAergic. So again, it plays a major role in terms of that kind of that brake pedal part of the central nervous system, keeping things under control. The most common neurotransmitter in the central nervous system is glutamate, and glutamate is very much of an excitatory neurotransmitter, and glutamate is actually a precursor to GABA, so a decarboxylase will convert glutamate to GABA. So you have the most common inhibitory neurotransmitter, GABA, made from the most common excitatory neurotransmitter. The glycine and the GABA can open up chloride channels, which is going to be inhibiting EPSPs. So you have several types of GABA receptors, two basic types. You have a GABA A and a GABA B. The GABA A receptors are inotropic. These are the ones that are going to be allowing chloride to possibly go into the cell. GABA B is going to be metabotropic, and it has a complex downstream biological effect. But as far as chloride is concerned, the GABA A is it. And as we've said before, if you have a depolarizing event on a neuron and then you have another neuron coming in, it's releasing GABA or glycine, opening up chloride channels, chloride is going to fight that EPSP and tap it down and possibly even creating an IPSP. So that again, we've talked about this before, so I won't rehash all that, but that's kind of how that works. You have a number of drugs that will work as agonists for the GABA A receptor. You have a class of drugs called benzodiazepines, the trade name Valium, Xanax, Halcyon. All of these are going to be working on the GABA A receptor. And as you know, benzodiazepines are an anxiolytic. They're anti-anxiety types of drugs. So we'll just write this here. Okay, so that's one of the things that they'll do. They also can be used as a muscle relaxant. The benzodiazepines, each of them, whether it's Valium or Xanax or Halcyon, and there are others, they all have slight different effects, but they all work similarly in the sense that they will bind to a benzodiazepine binding site on the GABA A receptor. The GABA A receptor has many binding sites on it in addition to just GABA. So other binding sites are specific for other types of molecules and such. So there's a specific benzodiazepine binding site. So the benzodiazepine will bind to the GABA. Now, it's an agonist in the sense that it is going to promote activity there. Okay, it's going to potentiate GABA activity. So the benzodiazepines in and of themselves cannot open that chloride channel. So if all you have are just the benzodiazepines minus the GABA, then they're not going to open that channel. But if you have a GABA bound to that receptor and then you also have a benzodiazepine bound to that receptor, then it will increase the frequency of opening of that channel and possibly allowing more chloride to come in that would then inhibit excitation, you see. So that's kind of how that works. What it does in the theory behind anxiety is that there's, overactivity of certain brain circuits. So again, giving someone a benzodiazepine, in a sense, you're tapping the brake, you're slowing things down, and that tends to make the person feel a little better. Now, the benzodiazepines, you do get a buzz from them. So it will work on the dopamine system and other systems as well. And again, as always, I'm not implying that the only thing the benzodiazepines do is just simply affect GABA. There are downstream effects as well, because if you're altering GABA, then you're going to be altering the downstream neurons, which alters further downstream neurons, and you get all kinds of interesting effects. Like other drugs like this, if it is abused, eventually the, quote, buzz that you get from say, Xanax is going to attenuate, and it'll be less and less. You end up having to take more and more drugs to get the same buzz. Again, it's basically a path to nowhere for that. One of the other things that's interesting about the benzodiazepines are very, very helpful for some people. For some people, they have to have it to cope, whether it's panic attack disorders or just general anxiety or whatever. It can be very useful for many people. But it does have side effects. One of the side effects of benzodiazepines is that it causes problems in memory. So someone who is on a benzodiazepine longer term, maybe a relatively higher dose perhaps, they tend to have problems trying to remember things. So there's an amnestic quality about this class of drugs. It causes you to forget things. Now, to what degree you have that effect on a patient will vary from patient to patient. Some patients have a lot of problems with this. Other patients have less problem with this. But it's a fairly common complaint. And if you go on to the chat rooms of people that are, struggling with anxiety, and the street name is benzo, so I'm on a benzo, but the benzos made me stupid. What they mean by that is it impedes their memory function, making it very difficult for them to get along in their routine of the day. They end up writing Post-it notes to themselves, trying to remember from conversation to conversation what actually happened. So for some people, it's not worth it. So they'll take it, they don't like the side effects, and then they'll quit. Well, this drug is also a very dangerous drug in terms of quitting it. Because if you've been on a benzodiazepine, or the patient's been on a benzodiazepine for, say, a month or two, and it's a relatively high dose, if they were just to all of a sudden stop taking it, you're going to get what is called a rebound effect. We've talked about this before. Those receptors start down-regulating. In other words, those postsynaptic membranes that are being potentiated by the benzodiazepine, again, the biology is poorly understood, but that postsynaptic membrane will start down-regulating the GABA A receptors. So, again, that's a brake pedal, right? So what happens if you just all of a sudden quit, now you've just basically taken the foot off the brake, and now you accelerate. So the rebound effect, if someone is taking it for anxiety issues, is that not only will the anxiety return at baseline before they took the drug, it will be even more anxiety than they had before they started taking the drug. And that's a real problem for some people. So that's one of the downsides of dealing with the benzodiazepines. You have to be very careful when you stop taking it. Another more serious issue with the benzodiazepines is that it can cause seizures. Again, seizures is just a overactivity of the neurons of the central nervous system. So they've had this brake pedal pressed for months, and then all of a sudden you just quit taking it. Now the brake pedal is released, and the patient could go into seizures, which of course can be very damaging to the central nervous system. So again, that's another downside in getting off the benzodiazepines. So how should one approach this? Well, I think it's a little common sense in the sense if the patient has been on benzodiazepines for a while, and if they want to get off of it, you just don't quit taking it. What you have to do is you have to taper. You basically, working with your patient, okay, you went off the benzodiazepines, you don't like the effects. Okay, so we're going to want to reduce your dose for a little bit. You'll be in that lower dose for a week, and then the following week we'll reduce it a little bit more. In other words, it gives your brain a chance to adjust, to maybe put some more receptors in there as you start weaning yourself off of the drug. So when you're dealing with the benzos, you wean the patient off very carefully because you could have a lot of bad effects if you don't. In fact, the benzodiazepines also, because of the nature of what they do, can be used for individuals that are struggling with seizures. So that's, again, there are many drugs that helps with people that have seizures. So the benzodiazepines is one tool in the toolbox for that, again, because of their inhibitory or their braking features. So again, very common drug out there, very useful drug. Interestingly enough, the benzodiazepines are relatively safe. If someone were to overdose in a benzodiazepine, it's highly unlikely that that's going to kill them. It might make them very sick. It might make the patient wish they were dead, but highly unlikely to actually be life-threatening. Now, if you mix it with alcohol, all bets are off because alcohol and benzodiazepines don't go together. One potentiates the other. So that's bad news, of course. Another drug that interacts with the GABA A receptors is barbiturates. Barbiturates bind to the GABA. There is actually a barbiturate binding site. It's different than the benzodiazepine binding site, where they bind onto the GABA receptor as well, the GABA A receptor. It is more potent. Unlike the benzodiazepines, if you have a high enough level of barbiturates, the barbiturates can open the channels in and of themselves. Now, at normal doses, that is going to potentiate it similarly to what you have with the benzodiazepines, except in a more aggressive fashion. The barbiturates also interfere with a lot of other systems in addition to the GABA A receptors. The Barbiturates are also known to inhibit glutamate receptors, AMPA, and we'll talk about AMPA in a moment or in another presentation. AMPA receptors is a type of glutamate receptor. And so if the barbiturates is going to be inhibiting that as well, again, another mechanism. The barbiturates do other things in addition to even these two. So barbiturates, unlike the benzodiazepines, which typically is fairly specific to the GABA receptor A, maybe even be involved in some other things, but mostly GABA A receptors, the barbiturates do a lot of other things. Now, unlike the benzodiazepines, barbiturates, an overdose of barbiturate will absolutely kill you. Just flat out kill you. It'll kill you by depressing the respiratory center. So back in the day, barbiturates were used as a antidepressant. They were used as an anxiolytic, sleep problems, etc. So a lot of people that were despondent or whatever else, if they chose to end their life, they did it by ODing on barbiturates, and it's a very effective drug for that. Happily, it's very difficult to get barbiturates in pill form nowadays. There's no reason to prescribe anybody a barbiturate because we have better drugs. We have benzodiazepines, way safer than barbiturates. In fact, barbiturates are still used, but they're highly, highly controlled. Barbiturates are used controlling epilepsy or seizures. Again, very controlled. A lot of these drugs are given IV. Barbiturates are also used to euthanize small animals when I was research active, and I would do whatever I was doing to rats or mice, and it was time to sacrifice them or kill them to examine their tissue. The way I would do it, I'd just give them an overdose of our barbiturate, sodium pentobarbital. I knew the dose, pop them in their belly, and in about 2 minutes, they quit breathing and they're dead. So again, it's very effective in killing things, which is why it's a very dangerous drug, which is why you don't prescribe it really anymore. But it's still being used in medicine, but under a very highly controlled environment. General anesthetics are also used, and let me put it this way, general anesthetics are also interacting with GABA A receptors, so they're an agonist for that. So if you go into surgery and giving you a general anesthetic, completely knocking you out, that is going to work on this system as well. The bottom line is, though, if you ask an anesthesiologist exactly what's the mechanism by which these general anesthetics work, the answer is, I don't know. We don't know why it works. We know, and these are gases, we know that the gases will interact with the GABA A receptor, but they probably are interacting with a lot of other things that we don't understand. We don't really understand what's going on in the brainstem that causes the person to lose consciousness. When given this gas, this is just basically a lot of I don't knows. But what they do know is they know the protocol in terms of it being safe. So they know exactly how much to give. They know the regimen per body weight, per type of surgery you're doing, etc. So the protocols are very well defined. So these are very safe drugs, relatively speaking. But the actual neurological substrate that gives rise to rendering somebody unconscious, other than just kind of hand-waving, saying, yeah, that has something to do with the GABA A receptors, is basically unknown. Okay, so that's that. Glutamate, as I've already talked about, and aspartate, those are excitatory amino acids, and these are EAAs, you'll see that in the literature, and it is the most common excitatory neurotransmitter in the central nervous system. And so that's going to be one of my major accelerators in the central nervous system, and GABA is going to be one of my major brake pedals in the central nervous system. Okay, so we will end this here, and we'll pick up on nitric oxide next time. Last time we talked about GABA and glutamate, the major brake pedal and the accelerator in the central nervous system, and I was going to talk about nitric oxide next, but there's one little thing I left out with the benzodiazepines that I think is kind of interesting, so I just kind of do it up here. Benzodiazepines can be given for someone who is suffering from alcohol withdrawal. So someone who is abusing alcohol and they stop taking alcohol, their body is going to react because alcohol is just another drug, does many, many, many effects on the central nervous system. And what's useful for this is that, and may surprise you, many drugs you can have withdrawals, like heroin or things like that we'll talk about in a moment. And they will literally have your body go through a living hell during the withdrawal process, but you will eventually make it. It won't kill you, but you, again, might wish you were dead in terms of the withdrawal of, in some of these opioids. But alcohol is different. Alcohol is one of the few drugs where the person undergoing withdrawal can actually kill them. So the withdrawal process of someone addicted to alcohol can actually make them dead. And so it's pretty serious. One of the things that one could have in terms of alcohol withdrawal is going to be seizures, because alcohol is a depressant, so alcohol is a big brake pedal. And so when you remove alcohol into the system, if the system has been abused long term, the person could go into full-blown seizures and actually just take them out and kill them. So one of the common effects of alcohol withdrawal is called DT. And DTs is delirium tremens. And it is a whole host of physiological responses to alcohol withdrawal. So benzodiazepines can be a nice bridge drug that helps somebody get through the withdrawal process as they're going through, in a sense, kind of drying out. Again, lots of other drugs you can use, etc. I'm just pointing out that benzodiazepine is just one of them because of the seriousness of alcohol withdrawal to your health. Okay, so let's go back to nitric oxide. Nitric oxide is a gas. Nitric oxide can function as a neurotransmitter, but this is very different because a gas is not going to be bound by a membrane, so you don't have synaptic vesicles containing nitric oxide. Nitric oxide, its control is simply by generating nitric oxide. There is an enzyme called NOS, nitric oxide synthase, and basically you're taking nitric oxide, pulling it off an arginine amino acid. So if you want to control the nitric oxide, you control NOS activity. So nitric oxide, in terms of its functioning as a neurotransmitter, as it just goes right through the membrane and then will affect the downstream cells. It could be excitatory, it could be inhibitory, depends upon the biology of the cell that it is affecting. You're going to find this in the GI smooth muscles as a player there. You're going to find it as a player in the central nervous system as well. And basically what it's going to do is it's going to be altering the cell biology. A lot of times the nitric oxide is going to be altering the second messenger system. So it could be altering calcium levels. So also NOS is stimulated by calcium levels. So what you could also have is a situation where you have an increase or decrease in calcium levels, and that could turn around and affect the activity of NOS, which could turn around then and affect or cause generation of nitric oxide. The nitric oxide could go into the cell, and it can interfere or interact with cellular mechanisms, second messenger systems, causing changes in calcium. In other words, the biology is very complex. All my point here is that NOS controls nitric oxide, and nitric oxide is a player in the central nervous system. Now, nitric oxide should not be confused with nitrous oxide. Nitrous oxide is laughing gas that you would get perhaps in a dental office. That's different than nitric oxide. And you also may be aware from other courses, nitric oxide can be a very powerful relaxer of smooth muscles in certain situations. Okay, so I will leave that. Then we have neurotransmitters that are called peptides, and if it's transmitter, then we call a neuropeptide, anywhere from 2 to 40 amino acids. The neuropeptides, when they're a neurotransmitter, they're very different than the other neurotransmitters we've been talking about. All the other neurotransmitters we've been talking about, they are synthesized in the presynaptic terminal. The neuropeptides are not. The neuropeptides are made in the neuronal cell body itself because they're a neuropeptide. In other words, you're having to put together chains of amino acids, and that takes a lot of machinery of the cell to do that. So you have the Golgi complex, the RAR in the cell body, all the things that in the cell body that happens to package things into assembled proteins, messenger RNA, transcription upregulation, etc. So the neuropeptides are synthesized in the cell body itself, neuronal cell body, and put into a vesicle, and then the vesicle is transported down the axon until it gets into the presynaptic terminal. Now, the neuropeptide synaptic vesicle looks very different than the other synaptic vesicles. First of all, the neuropeptide synaptic vesicles are extremely large, way larger than the smaller vesicles that contain these other neurotransmitters I was talking about up to this point. And also, and again, it goes back to Dale's principle, which is wrong, which is you'll see in presynaptic terminals, you'll see synaptic terminals that have vesicles that have neuropeptides. And the other thing, too, is that the synaptic vesicle with neuropeptides tend to be very dark. So they have a different tone to them completely. So they're big and they're dark. But they'll be among other synaptic vesicles that are releasing other neurotransmitters. Again, going back to the idea that multiple transmitters can be released from the same neuron. And also what's kind of cool in terms of a measure of control is you have these neuropeptides in a synaptic vesicle, then you'll have the smaller synaptic vesicles that contain other things, other neurotransmitters. And whether or not the neuropeptide is released into the synaptic cleft will be a function of the frequency of action potential coming down the neuron. So it may be low frequency, you just have the smaller neurotransmitters being released, but if you increase the frequency to a high enough point, then you have both smaller neurotransmitters being released and the neuropeptides being released. Again, another level of control of this very complex system. So examples of neuropeptides would be endorphins. You probably have heard of those. Runner's high, you run and you get this buzz after a certain point in time. You say, oh, that's the endorphins talking. You say, well, what about the dopamine? Well, the endorphins are going to interact with the pleasure center, causing increase in dopamine. So it all kind of wraps up here together. So endorphins would be one. Enkephalin is another one. Endorphins are fairly big neuropeptide. It's about 40 amino acids, so it's a fairly quite large one there. Dynorphins is another one. Again, there are subclasses of these as well, but these are going to be considered endogenous opioids. Endogenous means that your body naturally makes it, and then you have opioids, which I think you have an idea of what that is. Now, one potential part of confusion would be that there's opioids and opiates. Well, what's the difference? Well, an opiate is defined as a drug that is derived from opium poppy. So opium itself, morphine, directly derived from that would be considered an opiate, but these are also considered an opioid. So the way to look at this would be kind of draw some circles here. You have a class of drugs, opiates. Okay, that circle there. And then what you have is what we would call opioids. We'll go green. Whoops, I didn't want to do that. Let's try that again. I meant to go green. Come on. Green, there you go. So these would be opioids. So an opioid is the whole thing. So an opiate is an opioid, but not all opioids or opiates. Because enkephalin, endorphin, dynorphin, those are opioids, but not opiates. But morphine and opium are opiates, but also opioids. So, said another way, opiates is just a subclass of opioids. So if you're not sure what to call it, just call everything an opioid and you'll be fine. Now, you have other drugs out there like oxycodone, fentanyl, some of those types of drugs. Those are not, and heroin is one, okay, heroin. Commonly, heroin is considered an opiate, although the contents of heroin, not all the contents of heroin is actually derived from the opium poppy. Some of the components in heroin is from the opium poppy, but there are other drugs in there that are considered opioids that are not, so it's kind of a hybrid thing. And then when you start getting into the fentanyl, there's nothing in there that's similar to the opium poppy. So it gets a little murky in terms of is it an opiate or not an opiate. So fentanyl certainly would be an opioid. Not really be considered an opiate because it's not really derived from the opium poppy. But anyway, that's kind of how that works. So all of these drugs, of course, are highly addictive. They can be very useful. Morphine, very commonly used as a powerful analgesic. You go in the hospital, you have pain, of course, they're going to hit you with some morphine. Again, very powerful, very helpful for that. Of course, heroin can do the same thing. But these drugs are easily abused. You'll get a buzz. They'll make you feel good, euphoria, which is why they're abused on the street. The problem is that your body massively reacts to these drugs such that you get significant alteration in your central nervous system when you use these drugs. And again, goes back to the classic downregulation of receptors, such that if somebody is on, say, heroin, they'll get the buzz, but the more they take it, the less buzz they get, the more drug they have to have chasing that first high, and before you know it, you're not getting much of a buzz from the heroin, but if you stop taking heroin, then your body undergoes withdrawal and you feel terrible. And I mean terrible as in pain, as in all kinds of physiological reactions that would be considered a living hell for somebody. So if you're talking to somebody who struggles mightily with opioid addiction, what they'll basically say, I started out taking the opioids for pleasure, but now I've moved beyond that, and I'm not taking them to feel good, I'm taking them not to feel bad. In other words, if they quit taking them, they start moving into that withdrawal. It's a hideous experience, so they go back to taking the drug, and therein lies the trap for that. So it's a tough one, and your body does have a pretty powerful effect in terms of downregulation of receptors and such. There are drugs that will help push against some of these effects. You have a drug out there called naloxone. Naloxone is an antagonistic drug. Now, why would that drug be out there? Because you can die from overdose. I think you already know this, but overdosing in morphine, overdosing in heroin, it can kill you. And again, a lot of people, unfortunately, sadly, do that. So if you're working with anybody who's a healthcare worker that deals with people who struggle with this type of addiction, they're going to be having naloxone somewhere in a vial, somewhere on their person, because someone's on the street, they've just OD'd on heroin, and they're about to die. You pop them with a naloxone, and it will bring them out instantly. It will literally save their life because it is an extremely fast-acting antagonist. It will immediately block the deleterious effects of the heroin and will save lives. And so that's a very important drug for people that work with individuals that struggle with this. There's another drug, buprenorphine. And it is actually a weak agonist for opioids. Or opioid receptors, and so it can be used to manage the withdrawal effects of someone withdrawing from an opioid. So what it does is kind of a bridge drug. So it kind of taps down. It doesn't have the potency of the morphine or the heroin or whatever they're taking. So it's it just kind of tapers down the effects and blunts some of that, and it helps people to get through the detox period. Another one that is used is methadone. I'm sure you probably have heard of that. The methadone is also an agonist. It's more powerful than that drug, but it also can be used as a bridge drug as well. So you have ways of modulating all of this. The opioids have a variety of receptors. The mu receptor is the one that you hear the most about, but there's a mu receptor, there's a delta receptor, there's a sigma receptor. There are all these other receptors, but most of these drugs will interact with the mu receptor, which again is an opioid receptor. Fact of the matter is, as far as neurotransmitters are concerned, most of the neurotransmitters that are amino acids or neuropeptides are non-opioid types of drugs. So most of the neuropeptides are not opioids. And again, a big long laundry list, so I'm going to just show a couple here. Substance P is one. It's found in the central nervous system. You also find it in the GI tract as well. You'll find it in the dorsal root ganglia. It's involved in pain transmission, but it's also involved in smooth muscle contractions as well. So it's a very common neurotransmitter out there. You have VIP, you have vasoactive intestinal polypeptide. It's typically is an inhibitory neurotransmitter involved in smooth muscle, and it's a big player in GI physiology. So again, just kind of a whirlwind tour of some of these other neurotransmitters. This is certainly not exhaustive by any stretch. I'm just kind of hitting some highlights so that you know kind of what's out there as far as neurotransmitters and receptors. Okay, so we'll pick back up on glutamate next time. I've spoken before about glutamate as a neurotransmitter, the most abundant excitatory neurotransmitter in the central nervous system. What I want to do is focus in a little bit more on the basic type of receptors for glutamate. And we have 4 basic type of receptors, 3 of which are inotropic. So we have an NMDA receptor, we have a kainate receptor, and we have an AMPA receptor. All of these are inotropic, which means that when glutamate binds to it, that it can possibly open up and allow electrolytes to pass through. You have a 4th kind of glutamate receptor, and this is going to be a metabotropic glutamate receptor, and it's just simply symbolized as an M glutamate receptor. And so, of course, it binds to this, and it's going to be, or the cartoon is indicating that it's showing that it's interfacing with second messenger system. So the biological effect of glutamate binding to this metabotropic receptor, it can be wide and varied, and it just depends upon the cell biology of the downstream neuron that is binding to as to what the effect would in fact be. So I'm going to talk a little bit more about each of these. So in literature, you're going to see the NMDA receptor being denoted as that, the kainate that, and the AMPA that, and of course the metabotropic that. So I'm going to talk, let's go ahead and talk a little bit about the AMPA and the kainate, and then I'm going to get into it with the NMDA receptor. The kainate receptor, probably the simplest one, and the kainate receptor, glutamate is going to bind to it, and it's going to open up and then allow sodium to come in and potassium to leave. And in the direction of those is simply going to be what is the membrane potential at that time of ion flow. So it's fairly straightforward in terms of how that works. It's named kainate because kainate or canic acid is a a chemical that will actually bind to these types of receptors, so it's more of a kind of an analog to glutamate in that regard. But this receptor is specific for canic acid and will stimulate this receptor. Then you have an AMPA receptor. Again, glutamate will bind to it and it will open up. Another aspect of the AMPA receptor that makes it a little different is that it also has to have zinc to bind to it as well. And so you got a zinc binding site, and then when zinc is bound to it, glutamate's bound to it, then it's going to maximally open up. Zinc, an important player in this particular type of receptor, and zinc can actually be released from the presynaptic terminal. So I'm going to go zinc released from the presynaptic terminal. Okay, along with whatever neurotransmitter is being released, in this case glutamate. And so you have an action potential, glutamate's being released, but along with glutamate, zinc will be released. It's just part of that in the fluid inside the vesicle. And zinc will actually potentiate, so zinc potentiates the opening of the channel when it's at relatively low levels. Now, experimentally, what has been found out is that if you really, really blast this with zinc, and which at very high levels, zinc actually at high levels will cause, keep this channel from opening regardless. That's more of an experimental type of thing because you really wouldn't have zinc that high that would cause that, but it can cause some interference with the functioning of this receptor if the zinc is too high. But in biological realms, zinc basically potentiates such that if you have zinc there, and of course it's going to bind because you always have some zinc, and it's going to help open this channel when the glutamate binds to it. And again, you're going to have your sodium and your potassium being permeable to that. The receptor that's the most interesting of all of these is the NMDA receptor. There's a lot going on with that, and I'm going to spend a fair amount of time on that receptor because it is thought that this receptor, the NMDA receptor, is incredibly important for learning, memory function, and so I'm going to elaborate on that a little bit more in a minute. So it has some really interesting characteristics. First of all, you've got your glutamate. It's going to bind to that. Another factor, though, is glycine also binds to it. So for this receptor itself, you have to have both glutamate and glycine to bind before the channel will open. But even if the glycine and the glutamate bind to it, the channel still will not open because of one thing. You have a magnesium binding site. So I'm just going to put an Mg here, Mg, that's docked, and as long as that magnesium is docked where it is docked, then regardless of whether you have glutamate and glycine binding, this channel will not open up because the magnesium is going to block any type of movement of the electrolyte. So what has to happen is the only time the NMDA receptor will open up is if the membrane potential around the NMDA receptor is depolarized to enough degree for a certain amount of time. So if you were to theoretically, if you were to have a postsynaptic membrane and the only thing in that postsynaptic membrane were NMDA receptors, and there's no other way to depolarize the membrane, then the membrane would never be depolarized because you could dump all the glutamate and glycine onto that receptor. It will never open up. The only way it opens up is if the membrane is depolarized for a sufficient length of time, enough to drive the magnesium off of its binding site, thereby opening up that channel. So what you have in biological systems is never just an NMDA receptor on a postsynaptic membrane. So typically what you would have say, a membrane here, and you would have either a kainate or an AMPA. I'm going to say K. you would have those receptors. Okay, they would be in the postsynaptic membrane. And of course, they're going to be binding to glutamate. And then you would have, I can change colors here, you would have interspersed in there NMDA receptors, such that now when you have glutamate being bound to these AMPA and kainate receptors, they're also going to be binding, the glutamate's going to be binding to the NMDA, but you're having these being bound. The binding of the glutamate will open up the AMPA kainate receptors and will allow then sodium to rush in, depolarizing the membrane. So it may, and I'm going to make numbers up, minus 70, going to go up to plus 60. And if the amount of glutamate is enough to keep this membrane depolarized for a certain length of time, then and only then will it drive the magnesium off of the NMDA, and then the NMDA receptors will open up and then allow sodium to rush in for even greater depolarization. So that's the key, is that the NMDA receptor is voltage sensitive. So you have to get it to have enough degree of depolarization of the membrane before the NMDA receptor will open up. Now, you can sit there and ask, well, so what? You got more sodium coming in, who cares? Well, here's the thing about the NMDA receptor that makes it so special, and that is the following, which is, in addition to allowing sodium to rush in, the NMDA receptor is very permeable to calcium. So when the NMDA receptor opens up, calcium flows into the cell. So if I have a way of elevating calcium levels in the cell that has the postsynaptic membrane, calcium is a second messenger system. So if I alter the level of calcium in that downstream neuron, that is going to cause biological changes in that neuron. So that's the power of the NMDA receptor, is that it can change the downstream neuron when it starts allowing calcium in. So to recap, if I have, say, just kind of a normal amount of glutamate coming in per the action potential frequencies coming in from the presynaptic membrane, it releases glutamate. It's going to depolarize the postsynaptic membrane, allowing sodium to come in, depolarize it. But if it's not enough, then those NMDA receptors just sit there and they don't open up. But if I have a lot of glutamate being released in the synaptic cleft, enough to keep that postsynaptic membrane depolarized for a long enough period of time, now I'm going to start opening up those NMDA receptors, allowing, of course, more sodium to come in, but it's going to start allowing calcium to come in. And when that calcium starts coming in, things happen. That downstream cell will, in fact, change. So that's the big thing, is the NMDA in its relationship with calcium. Now, I've mentioned this point before, and I'll say it again. With these receptors, they got binding sites for all kinds of molecules. So the NMDA, zinc is also a factor in terms of binding there. Of course, you have a magnesium binding. We'll talk about the PCP in a moment. But that's basically how all this works. So I think most of what I've just told you is in the narrative here, so I'm not going to rehash that because I think I've kind of told you that. So again, the point is I have to have a robust enough EPSP in the postsynaptic membrane to drive the magnesium off the NMDA, allowing calcium to come in, and then I have big changes. Okay, so let's tie this into how this would actually work relative to learning and memory. So when you think about having a memory, and I've got to greatly simplify this, but that's where we are on this. When you're having a memory of something, the memory is an electrical event, a certain pattern of electrical activity, a certain configuration of synaptic activities will occur, giving rise to your memory of whatever you're remembering. Now think about how you learn something. How do you learn something? How do you put something in a memory? Repetition. So you learn something, you rehearse it, it creates an electrical path, and then you remember it again, it creates that same electrical path over and over and over again until it's easier and easier and easier to stimulate that particular electrical path. I guess a goofy sort of analogy would be if you have a field and you walk from one end of the field to the other end of the field and you follow a certain route. After a while, if you follow the same route over and over and over again, a path of beaten down grass will emerge, and then that's the easiest way to get through the field. So something like that sort of goes on with the electrical circuitry of the brain. So if you're wanting a repeat of a certain electrical configuration, then you have what we call strengthening the synaptic connection. In other words, you want to make that synaptic connection easier for things to happen. You want to strengthen the synaptic connection. So how does that happen, and what does NMDAs have to do with this? Okay, imagine that we have a presynaptic terminal here. Those are my presynaptic terminal here, and this is glutamate's going to be in here. I got my little vesicles here, got glutamate here, 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 here. And over here, this is going to be a dendritic spine, a dendrite spiny process, or a spine right there. So what we have in the cartoon here, there's our NMDA receptor. They've left out the glycine for whatever reason, don't know. There's a magnesium. And then we have, and again, they're just having one of the other inotropic receptors. And so they have a Q and a K. The K is kainate. The Q is called quisquelate. I'll just write that out for you. Is a quisquelate receptor. A quisquelate receptor is another older term for AMPA. So I don't want that to throw you. So the Q, K is basically AMPA and kainate. Again, it's just saying, suppose we have one or two of those here. So now you have the configuration that I talked about last time, which is I have a way of depolarizing the membrane, which then gives me a shot of driving out that magnesium. So now if you have just a normal amount, say of glutamate, you have a few active potentials that are coming here, glutamate being released, but there's not enough glutamate that will stimulate this channel to open up because there's not enough glutamate to have a strong enough EPSP to drive that magnesium off, so magnesium is blocking. So you do have an EPSP here, but the EPSP's duration and strength is not sufficient to drive the magnesium off. Now suppose you dump in a lot of glutamate. Maybe you have many action potentials. Okay, the frequency is going way up. Now I'm really bombarding it with lots of frequency of action potentials. Now I'm having more glutamate coming through, a lot more glutamate. So the glutamate is so much that it is opening up these AMPA kainate receptors so that there's enough sodium rushing in to keep the membrane to be depolarized for a long enough period of time to where now the magnesium is leaving that receptor, allowing, of course, more sodium to come in, but also allowing calcium to come in. So now my calcium level is going up. And so if I'm elevating my calcium, I'm going to have a lot of cell biology happening. So one of the things they think goes on here is that with the calcium causes biological changes in the downstream neuron. And one of those is that there'll be a factor that is released from the postsynaptic membrane. This is the postsynaptic here. So I've got presynaptic up here, postsynaptic down here. That something is made that leaves this and comes back and talks to that presynaptic terminal. Now, the pretty good idea of what it is going to be nitric oxide. Now, we talked about nitric oxide being a neurotransmitter. Again, nitric oxides cannot be contained in the synaptic vesicle because it has no problem going through a cell membrane. So you control nitric oxide by controlling NOS, nitric oxide synthase. Remember, you're peeling off a nitric oxide from the arginine when this enzyme is activated. So it is thought that an elevation in the calcium causes an activation of NOS, and then NOS starts generating nitric oxide. Nitric oxide just starts diffusing everywhere because cell membranes, it doesn't make any difference. The nitric oxide will come into the presynaptic, and the nitric oxide will interact with a other series of molecules in the presynaptic terminal. And again, the biological nature of that presynaptic terminal will change, complements of possibly the nitric oxide, such that the next time you have action potentials, it will release more glutamate than it did before. So if you have, in normal situations, you have an action potential come down, it's going to release a certain amount of glutamate. If the nitric oxide comes here and changes the cell biology of the presynaptic terminal, now when the next action potential comes down, it will release an additional amount, a larger amount of glutamate. So we have, in a sense, a postsynaptic membrane or postsynaptic cell talks back to the presynaptic and causes more glutamate to be released per action potential. So we've literally strengthened the synaptic connection by releasing more glutamate. So that's one of the things that may be going on here. Another thing that seems to be going on is that with the increase in the calcium here, it can also alter the concentration of receptors of the AMPA kainate receptors on the postsynaptic membrane. So numbers of receptors goes up. So now I'm changing something in the postsynaptic and I'm changing something in the presynaptic, making it a much more efficient synaptic connection. Not only am I dumping more glutamate in, I've got more receptors on the other end. And that, in a sense, quote, strengthens the connection here. It is thought that this particular dynamic is critical for memory formation. So this leads us into another concept that's related. It's called long-term potentiation, called LTPs. And again, this is where your presynaptic, postsynaptic terminals change such that, again, you have a stronger connection when you have action potentials. And LTPs is a strong candidate for how memory formations are formed. Now, the LTP can last from hours, can last from days to weeks. So the question, or the answer is answering the question of how long do these changes stay in effect? And what I'm saying is it could be up to weeks that this could happen without reinforcement. So again, this all goes back to the ability of that NMDA receptor being able to allow calcium to rush in, changing the cell biology of both the pre and the postsynaptic membrane, strengthening that connection. A very, very important concept. Okay, I wanted to end up just talking, make a few more comments on some other things in terms of pathologies that may involve NMDA receptors. You have Huntington's disease, or Huntington's chorea is another name for that. That is an autosomal dominant neurodegenerative disorder characterized by motor disturbances, cognitive decline, neuropsychiatric symptoms, and it also will kill you. So note I said autosomal dominant, which means that if a parent has one copy of that gene, and of course, if you understand Mendelian genetics, then you got a 50-50 chance that the offspring will have that particular gene. And if the offspring does have that gene, they are also going to get Huntington's disease, and they will be dying a miserable death. There's no gradations of this disease. If you have it, you're going to die from it, and it's going to be a terrible experience. Now, what's a challenge with this particular pathology is that you don't show symptoms of the disease until you're in your 30s and 40s. So if you're 15 years old, if you're 20 years old, and you're carrying that gene, you have no symptoms, you have no idea you're carrying it. It's just that when you get into late 30s, all of a sudden you're going to start having some neurological issues, and then you'll have 10 or so years of just absolute misery, and then you die. The problem is that by the time you know you're carrying the gene, you've already had kids, typically. So that's the challenge with this. You don't know you have it until you've had your kids, and then they don't know they have it until they have their kids, and so forth, so on. So that's how this gene actually survives in the population. It's a very, very, very difficult situation. And if you have it, you're going to die from it. So we live in a day and age, though, where we can have genetic tests. So if a parent has Huntington's, you can then test your children, or the children can be tested if they wanted to find out, are they carrying it or are they not, because it's a 50-50. And if they are carrying it, they're going to die the same way. So we live in an age where we do have the genetic test, which raises interesting issues. Because then the question is, if one of your parents has Huntington's, and again, if they do, there has to be a family history of it. Okay, it doesn't just pop up. So you can trace back the family where you can follow the course of the Huntington gene. If a parent has it, the question is, do you want to know? So maybe your parent had it, which means you're 50-50 chance of carrying the gene. So the question is, you can find out because of our technology, would you want to know? And different people have different sensibilities on this. And one could argue all kinds of ways. Many people would say, yes, I want to have the test because I want to know how to plan my life. If I know I'm going to get sick when I'm 35 and die a miserable death, I might not want to be in school until I'm 35 and prepare for a career that I'll never have. Maybe I want to make some different life choices for that. Maybe if I know I'm carrying it, maybe I decided that I don't want to have children because I don't want to have a 50-50 chance of passing this gene along. Maybe if I know I have it, that's going to impact my choice in terms of my love life. I would think your partner would kind of need to know if this is in the offing. So a lot of life choices are to be made based on that knowledge, and a lot of people will choose to want to know. Some people choose not to know. Some people, basically, their mentality is, I'm just going to let life happen. If I get it, if I get it. If I don't, I don't. I'm just going to live my life as if I'm not getting it, and then just deal with the consequences. Those are all personal choices, but that does raise some interesting issues in terms of dilemmas of people, of children who a parent has had that. Anyway, lots of information on that in terms of literature if you're interested in pursuing it. But Huntington's, again, it's a tough genetic situation. And one of the factors that leads to this, they think, is because for whatever reason, you have an excess number of NMDA receptors, therefore too much calcium flow into the neurons, which, because of a variety of biological reasons, ends up killing certain populations of neurons, and then you have Huntington's disease. Another one of interest is going to be the phenylcyclidine, PCP. Remember, we saw a PCP receptor on here somewhere. Where was it? The other? Oh, there you go. There you go, PCP there. As you may know, PCP is angel dust. And so when that binds to it, it's going to inhibit the NMDA receptors. And for a series of biological reasons, that's going to end up having the effect that one gets when one has angel dust. Again, it's a drug of abuse, but that's how it works, is by shutting down or inhibiting the NMDA receptors. It is thought by some that NMDA overactivation may play a role in Alzheimer's disease. Alzheimer's is a complicated situation. I'd already mentioned earlier that you have some disruption of acetylcholine activity in your brain associated with Alzheimer's. So I'm nowhere saying that NMDA receptors causes Alzheimer's. What I am saying is that it may be one of many factors that contribute to the path of that disease, NMDA overactivation. Then you have ketamine. Ketamine on the street is called Special K. You get a nice little buzz out of it if you take it. It is commonly used as an anesthetic during surgery. It is an antagonistic molecule to the NMDA receptor, and it's going to bind at the PCP binding site to have its effect. The ketamine also interacts with other neurotransmitter receptors as well, so I don't want to oversimplify that. It can be used with opioids as an analgesic or pain control. One thing that's kind of cool is there's this new drug called S-ketamine, and S-ketamine has been shown to be a very powerful antidepressant treatment. And so what happens, and you wouldn't go with the S-ketamine unless you've gone through all the other classic antidepressant drugs. So this is kind of the last one on the list, but there's a lot of promise that given the patient, S-ketamine does help with depression. The ketamine can induce euphoria, which is why it's used, possibly by inhibiting dopamine reuptake. We've seen this before. You control the amount of neurotransmitters in a synaptic cleft, and the control there is in part by the uptake of it. So if you inhibit the uptake, you increase the level of dopamine, therefore amount of pleasure. We saw the same thing with cocaine, is it also inhibits the uptake of dopamine, thereby elevating dopamine. We're very sure that ketamine acts on a lot of other mechanisms as well to generate the effect that it has. The last drug of interest I want to talk about is nitrous oxide. Nitrous oxide is not to be confused with nitric oxide. Nitric oxide is that molecule we spoke of as being the retrograde type of transmission with the NMDA stuff. Nitric oxide is also a vasodilator, so it's a very active in interacting with smooth muscles, causing smooth muscles to relax in the peripheral vascular system. When somebody has angina and they're taking a nitroglycerin pill, again, it's releasing nitric oxide to relax the vessels of the heart for better blood flow, etc. So nitrous oxide is laughing gas. Okay, that's completely different than nitric oxide. And its activity is sought to go by inhibiting NMDA receptors. It also will stimulate dopamine, giving you a little bit of a buzz as well. It also is going to be playing on the opioid and the alpha-1, alpha-2 adrenergic receptor. So my point here is that nitrous oxide intermingles and has an effect on a lot of other different downstream molecules or receptors. Okay, last thing, and this doesn't have anything to do with these pathologies, but I just want to make sure that we all understand the concept of autoreceptors. Autoreceptors are such that, and I'll just kind of draw it out for you. So you have got an axon, presynaptic terminal, postsynaptic. So here's your pre, here's your post, and then suppose then I am having, receptors of a neurotransmitter sitting down here, okay? And so now neurotransmitters being released. You can also have receptors on the presynaptic terminal as well. And so what can happen is that if the level of neurotransmitter being released is enough, that will go around and start binding to the receptor on the presynaptic terminal. And so this is a way of regulating the biology of the presynaptic terminal. And it may be that these receptors here are metabotropic, and such it changes the cell biology in here, altering the amount of neurotransmitter being released. So an example of that would be norepinephrine. I'm just going to say norepi, released from, say, a sympathetic neuron, okay? And the sympathetic neuron, it will loop back around and bind to alpha receptors on the presynaptic terminal, which would in fact inhibit further norepinephrine release. So in this case, this would be an inhibitory thing. Too much neurotransmitter binds to autoreceptors, it dials down the amount of, in this case, norepinephrine being released. There are other situations with other neurotransmitters where the autoreceptors are not functioning as a brake, but actually would be functioning as a stimulant, so that if the neurotransmitter binds to it, it actually causes more neurotransmitter being released. So you got all these variations of control of the release of that neurotransmitter. So the autoreceptors is a very important concept in understanding that the system can modulate the amount of neurotransmitter coming out from that presynaptic terminal. Okay, so that's what I have here. The next section is just simply some problems. These are just concepts. I'm just putting these questions here to make you go back to the material and make sure you understand the questions being raised there. Okay, so that's all I have for now, so we'll pick up next time.